Hello, ladies and gentlemen. Lovely to see you all. We've got quite a packed house today, and we've got quite a packed programme. Reminds me of Thomas Beecham's comment about new works being played in the Royal Albert Hall, that a composer who had their work played first in the Royal Albert Hall was guaranteed a second hearing of it. So this is our Christmas meeting of the British Astronomical Association. I'm the President, David Arditi. First of all, I'll mention that we have a drinks reception afterwards, which has been organised by Hazel Collett and Mary-Louise Archer. So you're all invited to that. We've got various things on sale outside, which you can peruse in the break. We've got the NPAE stall and also the BAA calendars on sale and RAS diaries. We've got a bit of an echo. Do we have any new members of the BAA here who have never been to a meeting before, who would like to introduce themselves, and then I could formally welcome you to the association? Would anybody like to volunteer as a new member? You're not. Anybody? No? I will invite the paper secretary, Jeremy Shears, to tell us what papers have been approved by the council today for publication.
Thank you very much, David. No fewer than 6 papers were accepted, or 12 if you include all the repeats that we're about to hear. So I'll list the names, the titles of the papers and the authors. The rotation period and optical variability of the weak line T Tauri star, he pauses for breath here, RxJ 1845.5 minus 3750 by Bart Stiles and Josh Hampsh. The Brighter Comets of 2021 by Jonathan Shanklin. Miss Whitehead's Moon, an Edwardian Lady's Lunar Sketchbook by Nigel Longshaw. Noctilucent Cloud over Britain and Western Europe 2023 by Ken Kennedy. The Moon as Seen from Different Latitudes by Peter Geldart. And the 6th paper is Imaging the Sodium Cloud of Io by Chris Hooker. Thank you.
Thank you very much, Jeremy, and thank you for organising those. It is one of the unique aspects of the BAA that we publish papers like that by amateurs, and their work often gets referenced by professionals because it's seen in the BAA journal, and it's the only place where that kind of material is generally published by amateurs, or it's a few places that has a big tradition of it. I'll mention forthcoming events. There is, on the 11th of January, there will be a webinar for the Deep Sky section at 7:30, which you're all invited to. Then our next meeting here on the 20th of January, that's another Saturday, that will be another afternoon meeting at 2:30, 20th of January, Saturday. We will be having a special general meeting, and that will be to consider some proposed alterations to the bylaws. And if you want to know the details of those, they're currently on our website, and they will also be delivered with your next copy of the journal, with the December journal, which will be landing on your doormat, hopefully, in the next few days. The main provision there is that I'm hoping to change the bylaws so that we no longer have a special general meeting every spring where the members vote on the subscription levels. We want to transfer that duty to the Board of Trustees and the Council to take that decision. And there are a few other changes which you can read about. And if you want to discuss those with me, then email me. So that is the special general meeting. And after that, there are various talks. We have a general meeting where there will be some interesting lectures and sky notes. One of the nicest duties of the President is to give out awards, give out the medals and other awards, and we try and award them at this time of year. And we've got quite a few. We've got 1, 2, 3, 4, 5, 6 awards to give out. And I will ask each of those people to come up in turn, and they can say a few words if they wish about their awards. I'll introduce them and explain why they've had an award, and then we'll take a photograph. But we need to get them through them reasonably quickly. So first of all, the Goodacre Medal is awarded this year to Nick James. This is given in recognition of the recipient's contribution to the progress of astronomy over many years. Nick was nominated by Janice McLean and Lynn Smith. He has contributed for many decades to many areas of the BAA's activities. You all know him from the Skynote talks here. He's been paper secretary from 1997 to 2014. Since 2015, he's been the Comet section director. But his observational contributions cover a wide area: asteroids, near-Earth objects, supernovae, variable stars, rocket launches, almost anything that changes in the sky. He's a fund of knowledge on and a fund of expertise. And the Goodacre Medal is the senior award of the association. It's given for a lifetime's contribution to observational astronomy, and I think Nick is a very worthy winner of our most prestigious medal. So please come up and receive your medal, Nick.
This is where it falls on the floor. Thank you.
So, it contains a certain amount of gold, which has been formed in supernova explosions specially for you.
Absolutely. That's wonderful. So yeah, thank you very much. It makes me feel terribly old when I read the citation. But thank you, Pauline. You've been helpful. That's the second time you've been helpful today. I'm really proud of the BAA. The BAA has some faults, but I think it's a wonderful organisation. I'm really proud to be a member of the BAA. I'm really proud to have this award, which, if you look at the past winners of this award, are just an amazing catalogue of people in the BAA's history. So thank you very much to Lynn and Janice for proposing me. Thank you very much to Council for voting for me. And I really do treasure this. Thank you, everybody. I really am very proud to get this and very proud of being a member of the BAA.
Next, Paul Abel was nominated for the Stevenson Award. This is given for an outstanding contribution to observational astronomy, and he was nominated by former presidents Bill Leatherbarrow and Richard McKim. Paul has been contributing observations to the BAA for about 30 years. You'll all be familiar with his beautiful planetary drawings, but he's made contributions to the lunar, comet, variable star and solar sections as well. He's one of a small band who keep the tradition of accurate scientific visual observing alive. He's director of the Mercury and Venus section, which he's been doing since 2019 and been doing a great job there, producing regular newsletters and regular reports for the journal. So it's delightful to be able to give Paul Paul Abel, the Stevenson Award. The award consists of some money, which he's already had, and a this certificate. So come up and receive your award.
Well, thank you very much, David. I honestly, genuinely don't know what to say. And for those who know me, that's quite an unusual situation for me to be in. I would like to thank the people who nominated me, Bill Leatherbarrow and Richard McKim, who have provided me with a lot of help and assistance over the years. My partner, Matthew, who maintains the observatory and all the kit in it. If it was left to me, I suspect the telescope would never have come out of its crate. But also to the British Astronomical Association, a wonderful organisation that's really shaped my astronomical and scientific career, both professionally and as an amateur, for many years, and continues to support amateur astronomers regardless of their background or status, and long may it continue to do that. We're all very richer for having this organisation in our lives. Thank you, David.
Next, the Horace Dall Medal. This is given to those who show a marked ability at instrument making, and Stephen Floodgate and Dave Grist were nominated by John Archer and Mark Rushton for doing exactly this. They are long-standing members of Crayford Astronomical Society, and Stephen and Dave designed and constructed the Dobsonian telescope for the use by the Society at their public outreach events. The proposers described their telescope building as beautifully simple yet cunningly advanced. And these telescopes are a big attraction for the public at the events that Crayford hold. And audiences at the Winchester weekend have also heard about Steve and Dave's amusing exploits. So it's a pleasure to give them the Horace Dall Medal, which is in memory of one of the BAA's most distinguished past telescope builders. So Steve and Dave, are you here? You're Steve, aren't you?
I'm Dave.
Yeah, you're Dave. Right, that's the one for Dave. And Steve. Thank you. Would you like to say anything, Steve and Dave?
Thank you, Mr. President.
You're welcome.
Do you want to say? Oh, Steve. You're good.
Yeah, all right, but don't stand in front of the picture, the projector.
Can we just move along a bit?
Yeah, move.
Oh, right, okay. Yeah. Are we getting David in it? I think we should, Mr. President. Over there?
Should be.
Yeah. Go on,
Thank you. You sure, Tom?
Yeah, no, go on.
No one was surprised as myself and Dave that we got awarded this. It's not something that we expected at all. Very grateful to the BAA for this, and thank you to John Archer and Mike Rushton for nominating us. The telescopes that we've got and we use, there were 4 telescopes. If you've been to Winchester 2 years ago, you would have seen them. They were telescopes that were not being used or they were going to be thrown away. We built these new bases where you can actually be observing within 2 minutes of getting into the building. You lift them up, take them outside, you're observing, and they get used nearly every week. It has really rejuvenated what we do. Thank you to the BAA for this award. It's the first award I've received ever. In fact, the only award, I did receive one award many years ago, but to get that award, it was a bronze award, and I had to swim 25 metres in my pyjamas. So thank you so much to everybody for this. It's really appreciated, and we just hope that we get more people looking through the telescopes as we go. We do take them along to a lot of outreach things, and we took them along to the New Scientist Live exhibition, and we managed to get 2,500 kids on one day looking at Mars and Jupiter indoors. So, not a mean feat. Thank you.
Well done, Steve. Just a quick one from me. Thanks ever so much for voting for us, Council, and thank you, Mr. President. And are you sure you got the right people? When I look at what previous winners of this award have done, you think, well, how do we compare with that? But we get the message out there. It's not just for the people in this room, it's for those who should know about this subject and they're ignorant of it, and we can get that sort of fun. It's fun, if nothing else, and the involvement.
Exactly. It's lovely to see anybody building their own equipment still in this day and age when not that much of it anymore, and you're showing how nice it can be and how you can do something a bit different.
Thank you, David. And we'll wait. We name them all after famous people as well.
Thank you.
Come, Steve.
Don't go away, I'll need to see that. That one furry photographs.
Right. And now, one of our more recently instituted awards in honour of one of our most famous past presidents, Sir Patrick Moore, is the Sir Patrick Moore Prize. James Dawson was nominated for the Sir Patrick Moore Prize by Jeremy Shears and Janice McLean for his work both on encouraging public interest in astronomy and in contributing to the understanding of the history of astronomy. James is on the committee of Nottingham Astronomical Society, and he's been crucial to developing their observatory, both for the society and as a community facility. He spent many weekends doing construction and maintenance works there. He also often gives talks to the society. His other job is he's librarian for the Society for the History of Astronomy. He's developed and improved their library, and he opens it to visitors on his weekends and days off. And I'm told he's very strict if you don't return your book exactly on time. So, James, are you here? James gets a sum of money and also this certificate.
Brilliant, thank you.
I don't really want to say anything, but thank you for the award. I think Patrick passed away 11 years today, so I've worn this awful shirt in his honour.
I'm sure he'd be very...
Thank you very much, all.
Now, we have a prize which we've only awarded last year for the first time. This is called the Cicely Botley Prize. And this is for a notable contribution to the Association's publications. And Council voted to award it twice this year. We voted to award it to two people. And I think they're both here today, Anne Davies and Alan Dowdell. Firstly, we'll do Anne. Anne Davies is nominated by Janice McLean and Jeremy Shears for her long-standing work organising the writing and publication and production of the BAA's observing guides and other publications, and her work producing publicity material for the association, and as well as running our stalls at various events like Astrofest. And her proposers wrote, "Her function in this regard to the BAA is vital and often unnoticed, as it all just seems to happen. She goes about the job quietly and efficiently." So, Anne, please come and accept your certificate. And the prize is also a book token for £100.
Oh, well, spend that. Can we just take a photo there first?
Well, I'm grateful and surprised to receive this, but I think that Nick and Paul said how I feel about the BAA. But also I want to say that I have got so many friends since I've been doing this, and I thank you all for supporting me, and I hope I can continue doing what I've been doing in the past. Thank you.
And now the man who's been taking the photographs, somebody else will have to take a photograph of this one, Alan Dowdell. He's been nominated by Pauline Jackson and Philip Jennings for his 11-year stint of producing reports of meetings, like this meeting, for the BAA Journal. Each report is about 1,500 words plus photos, which Alan usually takes. And he's been doing that for 11 years, about 10 reports a year. Alan's also been organising the Winchester Weekend for many years, and you'll all recognise, I'm sure, his song-like reminder of keys at the beginning of every weekend. He's also been a section director in the past and done many other jobs for the BAA over a very long period. He's a stalwart of the association. So, this is the Cicely Botley Prize and the book token.
Thank you. Right. I've got copious notes to talk about. Anyway, I'd like to thank Council and President, and also to Philip for his support in giving me this award. Because I've been a member of 61 years of this association, I think it's got something good in. It is a wonderful organisation, like all the other people who've received awards. It's a wonderful organisation. But I knew Cicely Botley. She used to come along to the meetings, a little lady, very short person, used to sit in the meetings when we were at Burlington House. And halfway through a talk, she would suddenly shoot up and just, in a little squeaky voice, say something very important and then just sit down again. It was hilarious. We lost all these hilarious people in the association. But anyway, thanks to her and thanks to the association. Thank you very much.
Thank you very much, Alan. So I think we still do have some eccentric and maybe even quite amusing people in the association, and it'd be nice to meet some of you at the break times. So we'll get on to some science, I think, now. It's high time we got on to some science. And Professor Martin Hendry is here to talk to us. He's come all the way from Glasgow. In Glasgow, he is Vice Principal of the university and the Clerk of the Senate. He's a member of the LIGO Scientific Collaboration, which is a global team of many scientists who made the first, with their colleagues in the Virgo collaboration, made the first ever detection of gravitational waves, which was a discovery awarded the 2017 Nobel Prize in Physics. Martin is a fellow of the Institute of Physics and also Vice President of the Royal Society of Edinburgh, Scotland's National Academy. He's an advocate for science education and communication, and in 2015 he was given an MBE for services to the public understanding of science. And Martin Hendry is here today to tell us about listening to Einstein's universe, the dawn and exciting future of gravitational wave astronomy. So, Martin, give a hand.
Good afternoon, everyone. It's a great pleasure to be with you this afternoon. I think I spoke to the BAA Variable Star section first about 30 years ago when I was a postdoc in Sussex University. So all these years later, it's interesting for me to reflect on how much has changed in the world of astronomy in that time. As we heard in the introduction, I'm a member of the LIGO Scientific Collaboration. I'm wearing the sweatshirt just in case I forget that. And here is a slide which I won't spend long on, but just to emphasize that I'm not formally speaking on behalf of the collaboration today, but I will be drawing upon the expertise and good friendship of many, many colleagues across the world. There's about 1,700 members of the collaboration now, scientists and engineers and technicians that first of all make the detectors work. So I'm going to share some of that with you to begin with, and also carry out the analyses that has led to some of the exciting science that I'm going to share as well. So gravitational waves, in case you're not aware, are not electromagnetic waves. Over the last 100 years, we've grown accustomed to an opening up of the entire electromagnetic spectrum from the optical astronomy that we had done for hundreds of years to now spanning all the way from radio to gamma rays. But gravitational waves are a prediction of Einstein's general relativity that represent a whole new window in the universe, a different form of radiation altogether. So my talk is going to draw quite heavily on ideas about Einstein. He's something of a hero of mine. This is a photograph of me at Einstein's statue in the National Academy of Sciences in Washington from about 15 years ago. And you probably can't read the equations on the statue, but don't worry, this is just to emphasize that this talk is not going to be about equations. If you could read them, you would see some rather strange symbols in the top equation, because those are Einstein's field equations of general relativity, his theory of gravity. So I'm going to try and briefly just give you a flavor of what the underlying physics ideas behind that theory. Some of it, I imagine, you'll be broadly familiar with, because let's face it, Einstein is a very popular figure in the world of physics and astronomy. The middle equation, interestingly, is what Einstein actually got the Nobel Prize for. It's the equation to do with the photoelectric effect, which is important in the physics behind lasers, and laser is what the L stands for in LIGO, so I will talk about lasers in a moment. The final equation is the famous E equals mc squared, so I hope I can sneak that one in a bit later and it won't cause too much distress, because a little later in the talk we'll come back to the ideas of E equals mc squared and see what that tells us about some of the remarkable discoveries we've made. So lots about Einstein, and it's important to reflect on just what a major figure Einstein is. In 1999, Time magazine voted him Person of the Century, not Scientist of the Century, but overall the person who had most influence on the 20th century. I want to emphasize that was the editorial board's decision. There was a public vote as well, and the public voted for Elvis Presley. So you can decide for yourself who got that one right. But nonetheless, the famous view of Einstein as the sort of wizened old Yoda-like scientist with the white hair. Well, I'm kind of working on that. I don't know if I can compete anywhere near Einstein's scientific standing, but the hair's certainly going white. But in terms of Einstein's primary achievements, including his masterwork, his general relativity, he did a lot of that work when he was much, much younger. So I'm well past the point of no return in those terms. But I have enjoyed throughout my career at least trying to share ideas about general relativity with a variety of audiences. And not to shirk the fact that it is a complicated theory. It's probably one of the most difficult topics that we cover in our undergraduate degree at Glasgow. And nonetheless, it's an important one to share, because despite it being about 100 years old, and in fact it celebrated its 100th anniversary in 2015, the very year that we discovered gravitational waves, nonetheless, it's a very modern theory in terms of the ideas that we're still unpacking in terms of the impact on our lives. Everything from the GPS satellites running at a different rate because they are 40,000 kilometers above the Earth, compared with the rate at which gravity flows down here on the surface, where the gravitational field is stronger. The rate at which time flows because of that stronger gravitational field, I should say. So how can I describe general relativity in just a few words? You've probably heard this phrase before in some form or another. It goes back to not Einstein himself, but to John Wheeler, who captured the notion of Einstein's theory of gravity as space-time tells matter how to move, and matter tells space-time how to curve. And it's often also capturing the idea of space-time curvature a little bit like a rubber sheet, like a trampoline. It's a far from perfect analogy. It leaves out a lot of the detail, but for me it's always worked as just giving a nice visual way to think of how gravity bends space and time, and consequently the experience of gravity close to a massive object like the Earth effectively will cause the moon, for example, to follow a circular orbit because it's following the natural contours of space-time. And you've probably all seen those demos that you have at science centres where you can roll marbles around on that kind of curved surface to simulate everything from a gravity well for, you know, the Earth to indeed a black hole, which we're going to be talking about in just a few minutes. So that's fine if you've got that static rubber sheet. What if the rubber sheet is itself changing? Because after all, if you jump on a trampoline, you're not just going to jump up and down, but the trampoline itself will wobble. And that's essentially what gravitational waves are. They're ripples or wobbles in the fabric of space-time when the gravitational field changes. So gravitational fields are caused by space-time curvature, and changing gravitational fields caused by changing space-time curvature will produce gravitational waves. In that sense, it's not so different from electromagnetic waves, which are produced by changes in the electric and magnetic fields, but the mathematics is a little bit more complicated. So we'll steer clear of any equations, as I said, but I do want to share some numbers with you because the numbers are quite mind-blowing. Basically, that space-time rubber sheet, like a trampoline analogy, well, put it this way, it's a lot stiffer than any trampoline I've ever been on. If we think of the stiffness of space-time as to how it responds to a changing gravitational field, then me waving my fist technically produces a changing gravitational field and hence produces gravitational waves. But we couldn't ever measure them. We really need the universe to provide a cosmic laboratory to shake up space-time enough that we have a fighting chance to detect the ripples produced. And as they spread out through the universe, the job gets harder, which means to detect gravitational waves produced by a typical cosmic event, the events we'll describe in a few minutes, things like colliding black holes or colliding neutron stars, then the shaking up of space-time in our patch of the universe, by the time they reach us, just like ripples spreading across a pond, will produce movements less than 1,000th the width of a proton, or maybe somewhat more familiar, take the width of a human hair, you're talking 1,000,000 millionths the width of that. So how on earth are you going to measure a disturbance like that? Well, how on earth is rather crucial, because the real issue with detecting gravitational waves on Earth is that lots of other disturbances could swamp that signal altogether. And yet that remarkable sensitivity, 1,000,000 millionth the width of a hair, in the change in the gravitational curvature, is precisely what the LIGO detectors can do. So what do they do? How do they do it? LIGO stands for Laser Interferometry, Laser Interferometer Gravitational Wave Observatory. We'll get to LISA at the end. That's where the S comes in. But LIGO, these are ground-based facilities. There are 2 in the US, 1 in Louisiana, 1 in Washington State, 3,000 kilometers apart. They're L-shaped, and the arms of the L are 4 kilometers long. And what's going on in those L-shaped arms is that laser light of a very precisely known frequency is being bounced back and forth along those arms, so split into 2 beams that go off at right angles to each other, reflected off mirrors, recombined. In reality, actually, the signal is cycled within the arms hundreds of times to effectively increase the path length, but the basic idea is what the cartoon on the left is showing, which is when a gravitational wave passes by, it will stretch and squeeze the space-time in which the arms of the detector are sitting, and consequently, the path traveled by each beam will be changed. And that means that the laser light will change its degree of being in step with the other laser light that's going along the other arm. That's where the I comes in, the interferometer. It's an interference pattern we're looking for. We're looking for the interference of the 2 light beams and a change in that interference pattern as a kind of trigger, as a signal that the arm lengths are being changed. And the passage of a gravitational wave in the animation on the right, it's a little cartoon, as what would happen if a wave was coming out of the screen towards you. Well, Don't worry, of course, and you would barely notice. In fact, you wouldn't notice at all because that's enormously exaggerated. Remember, 1/1,000,000th the width of a human hair. It's a tiny, tiny effect. It's equivalent, to put it in other terms, with the width of a hair compared with the distance to Alpha Centauri. That's what we're trying to measure. But the pattern we're looking for is, it's called a quadrupole. It's that stretching and squeezing. When one direction is stretched, the other is being squeezed, is being shortened. So that pattern is rather distinctive. It's a prediction of Einstein's theory. Now, the sensitivity of the detector to these tiny, tiny changes is not the same across all frequencies, just like most electromagnetic detectors in astronomy have a varying sensitivity with frequency. So the way we represent that, again, a rather complicated looking diagram, but the key thing to take from it is just that we've got this kind of sweet spot around frequencies of a few hundred hertz, a few hundred cycles per second. The sensitivity is less good at low frequencies or high frequencies. The way we measure that is called the strain. It's the fractional change in the length of the arm caused by a gravitational wave passing by. And the trouble is, lots of other things can potentially change the length of the arm. So our ability to extract a gravitational wave signal is limited at low and high frequencies by all those other things. Again, there isn't really time to go into the details of that, but I'll be happy to answer questions as best I can about that. That's really where my colleagues in Glasgow have done a lot of the heavy lifting, because for decades they were developing the technology to get that curve as low as possible, to kind of keep the noise down, in other words. But that patch in the middle, a few hundred hertz, is the sweet spot where we've got our best sensitivity. And that corresponds to frequencies that the human ear can hear, which is why I called this talk Listening to Einstein's Universe. Gravitational waves are not sound waves, but we can render them as sound waves. We can think of them as if they were sound waves and effectively think of listening for a signal of a few hundred hertz when there's a lot of background noise. So an exercise I often do with school kids, especially primary kids, they love this one, is just to encourage them to make as much noise as they can. I could ask you to do that, but you're being terribly polite and listening to me. But if you go into a classroom and do that, and then quietly say something, maybe with my back turned to them, of course, no one can hear what I'm saying. But if I then say, shh, let's keep it quiet for a moment, they can hear what I'm saying. And even better, if I give them a list of phrases, and I say, I'm going to say one of these secret phrases, see if you can work out which one, they can normally do very well indeed. We're all quite good at that, you know, at a cocktail party or something, lots of background noise. If you know roughly what the person you're talking to is saying, you can usually fill in the gaps. So a lot of the progress in our field was made not just by the instruments becoming more sensitive, but also our understanding of what the signal should look like or sound like. So that's a pattern that you see here, kind of a theoretical one, we call a chirp, where the frequency increases, that's them getting bunched up as we go from left to right, and the amplitude or loudness increases as well, so that's stretching out in the vertical direction. That's the kind of pattern you would expect when, for example, two black holes coalesce with each other. They're spiraling in towards each other, giving off more and more gravitational waves as they get closer and closer together. And then when they merge, you get a sort of peak disturbance, and then space-time wobbles a little bit more, things settle down, and you're back to having just one black hole. So that's what we were looking for or listening for. The challenge was how to keep the noise down so that we could actually do it. And our development of that technology, again, I had no personal part in this, but I stand in awe of those who did, including many of my colleagues in Glasgow, working with others across the UK to supply to this largely US-funded project a really key technology development to improve the sensitivity of the detectors by effectively keeping that noise down. By replacing the steel wires suspending the mirrors at the end of the arms, which had been used initially by LIGO, replacing those with silica fibers, glass fibers, which don't wobble so much, basically. So that was a key development that began in 2010. It took 5 years to install these upgrades, and then by 2015, September 2015, September 14th, 2015, to be absolutely precise, this is what we were able to detect with our newly upgraded advanced LIGO detectors. It's probably quite tricky to hear, but in a way that's perhaps the point, so we won't ask for the volume to be increased. Let me just advance it a little and I'll freeze the animation so we can look at the pattern as well as listen. What you're seeing there is the signal detected by LIGO Livingston in Hanford. It's got that generic chirp-like pattern, the frequency increasing, the amplitude increasing, and then it fades away. The really standout feature is how similar they are in the two detectors. These are 3,000 kilometers apart, remember. That immediately told us we were onto something, because the chances of this just being random noise when the detectors are so far apart was immediately lower. And I'll play it again, because in fact what I'm doing is playing the signal over and over again. And what I'm also doing, one of our colleagues in Glasgow, Chris Messenger, produced this video for the first detection. It's a bit like what we do sometimes in optical astronomy with false color images. Firstly, you're hearing the signal rendered as a sound wave in the original frequency range, and it sounds like a rumble, which is the background noise, and a bit of a dull thud, which is the two black holes colliding. Doesn't sound terrible. It sounds a bit prosaic, that. But if you shift to somewhat higher frequencies, it becomes easier to hear, a bit more chirp-like, and the collision, the actual signal is a bit like that. Sounds a bit like one of my daughter's guinea pigs from a few years ago as well. Actually, sometimes I used an actual clip of the guinea pig. I can assure you these are definitely not cosmic guinea pigs, but we'll talk in a moment about what they are. But let's just have a listen to that signal again first. So I'm looping it twice at the original frequency range and then twice at the shifted and then looping the whole thing again. The reality was the signal only lasted for about a third of a second and then it was gone. So it's immediately easier to pick out what's going on if you just keep repeating it over and over again. We didn't have that luxury. But all of that basically convinced us over the 5 months between September 2015 and February 2016 that we had indeed detected gravitational waves. So what we believed we had detected was this, as I've said, this chirp-like signal replicated very, very similarly in the two detectors, caused by, and this is where the analysis would allow us to interpret what's going on in those red and blue curves, the spiraling in, the getting closer together of two black holes, the merger, and then space-time wobbling a bit more. We call it the ring down as it settles down. A bit like when you ring a bell, you'll get a sharp note, but then it will fade away. Now, how exactly we extract that information from the curves below, I'm just going to share with you a very short video clip from my colleague Laura Nuttall from the Institute of Cosmology and Gravitation in Portsmouth. It's one of the videos that we use in schools outreach, and again, it's very short. I'll let Laura tell the story of how we do the kind of pattern matching.
2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
Okay, so again, the devil's in the detail, all the scary equations we have to use to extract that information in a more quantitative way, but the essential principle is just about pattern matching what we expect to what we actually got. Now, that's all reliant on general relativity being the correct theory of gravity, so what we also want to do is test whether the data do look like what the theory predicts. So I want to next, look at some of the astrophysics that we've been able to deduce from all of that analysis. Well, again, at the very top level, one of the first things that we could immediately deduce was that all of this happened a long time ago in a galaxy far, far away, as you might say, because in fact this signal was coming to us from more than 1 billion light years away. And what we envisaged was happening, again, channeling Hollywood maybe a little for this animation, is two black holes barreling around each other, and in just that small fraction of a second, releasing a huge amount of gravitational wave energy, represented by the red spike there. So we could measure the masses of the black holes, again, just channeling the kind of methodology that Laura was briefly summarizing. And what we found was that the two black holes appeared to have masses that matched about 29 times that of the sun and 36 times that of the sun. In total, that makes 65, but the final black hole left behind had a mass of 62 times the mass of the sun. So in about 1/3 of a second, the equivalent of 3 times the mass of the sun, that's 6 million kilograms, was released in gravitational wave energy. Now, I promised you we'd come back to E equals mc squared. We can work out how much energy that amount of mass corresponds to. You just take 6 million kilograms and multiply by the speed of light squared. So there's a lot of zeros. It's a big, big number. But you can go one step further. You can turn that into a power by dividing by roughly the length of the signal. And what you find is something that even all these years later, I still find truly mind-blowing. Because that power in the form of gravitational waves is about 50 times the light power, the luminosity of every star in every galaxy in the entire universe. So the physics of this takes us back to that point I made about the trampoline of space-time being incredibly stiff. It's very hard to measure gravitational waves, but when they are produced, you're releasing a heck of a lot of space-time energy. Now, all of this almost certainly happened without any electromagnetic radiation being given off at all. So we really are, in a sense, probing the dark side of the universe. And I think it was Darth Vader who said you should never underestimate the power of the dark side. And I hope that little calculation we just walked you through emphasizes that he was, in fact, correct. Well, I'm not going to argue with Darth Vader anyway. So all of this, as was noted in the introduction, led to the award of the Nobel Prize to 3 of my senior LIGO colleagues in 2017. In fact, 6 years ago yesterday. So very timely, that's when the award ceremony took place. And I'm very pleased that they explicitly acknowledged in their speeches, in their lectures, the contribution that Glasgow and the UK had made to improving the detector sensitivity. But of course, the story didn't stop there. So again, time is short. Let me, in the final part of my talk, bring you up to date, and if time permits, say a little bit about what lies ahead. So in 2017, the other major development was that a third detector began operation. This is Virgo, mentioned in the introduction. They are based in Italy, close to Pisa, and their advanced Virgo detector operates in a very similar way. But the real beauty of having 3 is that this allowed us to determine the sky position of the gravitational wave signal rather better. When you have 2 detectors, the way you get information about the sky position is based on the slightly different arrival time of the signal in one detector compared with the other. So the Hanford and LIGO detectors saw our very first detection 7 milliseconds apart. And that gives us information about where in the sky the signal could have come from. It's all that high school trigonometry you probably don't want to re-engage with. But basically, you can turn it into working out a ring on the sky where that time delay would be the same from any point in the ring. You can't tell where in the ring the signal came from. You can use polarization to improve things a little, but that's roughly speaking the limiting factor. But when you have 3 detectors, that's 3 pairs, 3 rings, and where the rings intercept, Bob's your uncle. That's where the signal came from. So when Virgo began operation on August 1st, 2017, within 2 weeks, we had got a black hole merger that was localized about 10 times better than the previous black hole mergers, including the first one that we've just been talking about. So instead of 600 square degrees or more in the sky, we were talking like 60 square degrees. Still a big chunk of sky, but a lot better than hundreds and hundreds of square degrees. And just a few days later, on August 17th, 2017, we got another detection, which again, I imagine you've all heard about, which is the first binary neutron star detection. How do we know this was a neutron star pair and not a pair of black holes? Well, there are several reasons. Firstly, the signal was a lot longer. So here it is again, rendered as a sound wave. And that's consistent with what Laura's video said. The lower masses means that the signal takes longer. And then the ping we heard just a second or two after, that's the point in time when we received to the Fermi and integral satellites a big chunk of gamma rays. And they came from the same direction in the sky as this little animation will illustrate. Overlapping where LIGO and Virgo had pinned down the location, there were just a few dozen galaxies within that patch of sky. So our colleagues in various ground-based telescopes were able to identify a new star, or a new object, a remnant of that binary neutron star collision within the galaxy NGC 4663. And also, associated with it, as I said, was the gamma ray burst. So, of course, it's just an artist's impression. Who knows really what it would look like? But you've got the jets of the gamma ray. You've got information coming from that. You've got the remnant optical object that's known as a kilonova, which was, I think I said 4663, 4993, the wrong galaxy. And that's a sort of before and after picture of that little galaxy. This was a huge electromagnetic observing campaign in response to the alert that we had put out. And already, within just a matter of a few months, we were able to start churning out some really interesting astrophysical results based on these observations. Firstly, because the gamma rays and gravitational waves arrive so close together in time, well, we believe that's because the gamma rays set off about a second or so later, that actually they travel at the speed of light. But even if you know, that's an assumption, even if you then just take the data and say, well, this was 130 million light years away and they've only got out of step by 1.7 seconds, that means the speed of gravity and the speed of light must be pretty darn similar to each other. So that was a very important result. Another one, the one that's probably closest to my own heart, because I was deeply involved in this, was using the distance to the gravitational wave source to estimate the Hubble constant, the expansion rate of the universe, which many of you will be well aware has been a little bit of a thorny topic in recent years. So our measurement was not terribly constraining from just one event. We got the redshift, the velocity from the host galaxy. We got the distance from the gravitational waves. Our estimate is that blue curve, so very broad, very uncertain, but straddling the two different methods that are giving inconsistent results that has led to what people refer to as the Hubble tension. So at least we were in the right ballpark, and that has been a chief focus of what we've been doing since. So again, I will try and share just a few comments on that before I wrap up. I know we started late, but I'll try and talk for no more than another 10 minutes, so there's time for questions, maybe even a bit less. So, to bring you fully up to date, in 2018, we published our first catalogue of events, 10 black hole mergers based on our estimates of the masses, and 1 neutron star merger. I was overseeing our social media and communications for the collaborations at that point, and we thought a good tagline would be to say that our catalogue went up to 11. So those of you who are Spinal Tap fans might appreciate that. Our catalogue since has grown considerably. So let's tell you a bit about what's been happening in the intervening years. So these initial runs ended actually in 2017, and then it was April 1st, 2019, after some upgrade work, when we resumed detecting. This is our third observing run. And what was critical about that, as many of you might be aware, is that we started putting out candidate event alerts in real time. So those were publicly available. They were available via a web server and a web interface called GraceDB. But also we had an app so that you could access them on your phone. You could get woken up in the middle of the night, as I frequently was, when another candidate event came in. So all of that led to a huge further growth in the catalogue we have, now totaling 90 gravitational wave events. That catalogue was first published on the archive 2 years ago. There's a lot of back and forth with the journal. I believe it's now finally out, and that was led by one of my Glasgow colleagues, Christopher Berry. So he did a fantastic job getting all that work over the line. So there were a few standout events from that catalogue that maybe merit just a few seconds of mention. There were examples of black hole pairs where one black hole was a lot smaller than the other, a lot less massive, and what that gives you is a much richer structure in the gravitational wave signal. It's a bit like having extra harmonics in a musical note, to continue the listening analogy. There was also an example with another big ratio difference between the big object and the small, and so much so that we didn't actually know whether the small object was the lightest black hole we'd found or the heaviest neutron star. So that was in 2017. bit of uncertainty, sorry, 2019, bit of uncertainty there. There was another event which was the first example of what we call an intermediate mass black hole merger, where the black hole remnant was over 100 times the mass of the sun. And that's, loosely speaking, too big to be explainable in terms of the two that produced it having come directly from a core collapse supernova. What it suggested maybe was more likely is that perhaps this was a kind of hierarchical series of mergers. Two smaller black holes merged into bigger ones, and then they in turn merged. And, that's not so ridiculous, because if we've got supermassive black holes at the hearts of almost every galaxy, you've got to make them somehow. So this could be a kind of missing link in that story. Lots more to learn about that. There was another pair of neutron stars that we detected, but this time without an EM counterpart, probably just because it was too far away. We got very lucky in 2017. We hope to get equally lucky again, but not quite yet. We also did get to, in early 2020, real nailed-on examples of neutron star and black hole mergers. And those were interesting too. These are simulations on the right-hand side of the kind of signal you would expect. So what we're going to do is zoom in a moment on the kind of signal. So in the top left corner, you've got your neutron star and black hole. Notice that what's going to happen to the orange neutron star, the color doesn't mean much, but notice it's just about to be swallowed just about whole by the black hole. Whereas the lower animation, which unfortunately is just finished, I didn't talk fast enough, but let me just run it one more time, it'll only take a moment. What's happening there is that the neutron star is being kind of tidally stripped, it's being torn apart. So basically, the details of how the neutron star gets shredded by the black hole can tell you something about the interior structure of the neutron star. It maybe also could tell us something about the kind of astrophysical environment in which the merger happened in the first place. But for these two events, as I like to say in outreach talks, what we found is that the collisions were much more like Pac-Man than Cookie Monster. Cookie Monster being a notoriously messy eater, but nonetheless an event like that in the future could be incredibly useful in telling us something about the interior structure of neutron stars. Now, there are other ways to work out the interior structure of neutron stars. There are ways where you basically look at an isolated neutron star, a bit like the Crab Nebula pulsar that Jocelyn Bell detected, and look at how its spinning down tells us about how strong the crust of the neutron star is. But we have been doing that kind of thing from radio waves, looking at the change in the rotation rate from radio observations. Now we can do it using gravitational waves as well. And there's a whole series of papers that have put better and better constraints on how round the neutron stars have to be, because if they were any less round, then they would have given off gravitational waves that we would have detected already because of their asphericity, because of them having effectively a kind of mountain on the surface. That's pretty cool stuff. We've also been looking for a background of gravitational waves coming from the Big Bang. Bottom line is we haven't found one yet. That's a really, really difficult thing to measure, but a whole series of papers trying to put limits on how strong it could be. We've also been looking for more exotic things. I mentioned before about black holes coming directly from a core collapse supernova. I mentioned about there being an upper limit for that. There's a lower limit as well. And if we found black holes merging which had masses less than a solar mass, we don't think they could have come from a core collapse supernova. So they maybe could come from something more exotic, like primordial black holes from the Big Bang, or maybe formed out of collapsing dark matter. Again, we haven't found that yet, but we're looking hard for that. So I've mentioned the catalogue that our colleague Christopher was involved in. I said that was published initially in the archive 2 years ago. All of this data is publicly available. Let me skip a few of the results from the catalogue, just again to allow me a few minutes to just say a word or two about what's coming next, and then to allow a few minutes for questions. So we're now in our 4th observing run. There was a lot more commissioning and upgrade work done in between. The goal of going to our 4th run has been to push the kind of horizon distance within which we can detect gravitational waves yet further out. So that, of course, means that we expect to detect more candidate events. And that indeed is borne out by what's been happening. Let me skip this one again just to save some time. So we started on 24th of May. We're running for 20 months with a 2-month commissioning break. And whereas in the third run, we were getting, in the end, detections about 1 every 5 days, it now looks like we're getting 1 about every 2.5 days or 2.8 days. So our sensitivity's improved. Now, those are not yet confirmed, but there's a lot of candidate events where we've shared the information with EM partners precisely so they can go look for any EM counterpart. So stay tuned for lots of new results papers once we've done the analysis on all of these candidates. But bottom line is we're looking for another step change in the number of events so that by the time the 4th observing run is over, we should be looking at somewhere like about 200 events in total, and maybe a little bit less, maybe even a bit more. What about beyond that? Well, there'll be another gap, and then the 05 observing run will take us through to the end of the decade, more or less. And that will also see the CAGRA detector join. In fact, CAGRA should join during 04. That's in Japan. And then towards 05, we'll be looking at another LIGO detector, this time in India, joining. Now, why all these extra detectors? Well, the more you have, the better you can pinpoint the sky position. And that's good news if you want to look for an EM counterpart. So that's going to be the case for the neutron star mergers and hopefully the black hole neutron star mergers. Black hole mergers, probably no EM counterpart, but we ought to look anyway, just in case. So all of that will be assisted by the extra detectors. And then into the early 2030s, there are further ground-based upgrade plans. Again, you know, I'll share the slides afterwards. You're more than happy to get in touch with me if you've got questions, but I won't try and read all the detail on that. Much better to try and use a picture. And let me emphasize that as we move into the mid-2030s, we'll be looking to build a new generation of detectors altogether in the ground that will push even deeper into the universe. Really probably to the point where, beyond that, there weren't any black hole and neutron star mergers because there weren't any black holes and neutron stars yet, because the stars in the galaxies forming at that time, the kind of stuff that James Webb is finding now, had not been around long enough to produce those post-main sequence stellar remnants. So the instruments that will do all of that are, of course, not funded yet, but the design studies are well underway, indeed have been for some years. One is called the Einstein telescope, which is a somewhat different design, possibly, although that's not certain yet. And it could be in either Sardinia or somewhere on the German-Dutch border. So that's to be decided as well. And there's another project called Cosmic Explorer, which will be in the US and could have arms as long as 40 kilometers, so 10 times longer than the advanced LIGO ones. And again, all of that, remember that odd curve with the sweet spot in the middle? So it's just about getting that noise floor down lower and lower and lower. So it will just, you know, push us further out into the universe. But I would feel bad if I didn't at least spend a few seconds on this slide, because just like I began by emphasizing the whole breadth of the electromagnetic spectrum that's opened up amazing new windows for astronomy, similarly, there's a whole gravitational wave spectrum as well. And all I've really talked about is the very high frequency end of that. So one of the other windows is the lower frequency window that LISA, the Laser Interferometer Space Antenna, will probe. We hope that LISA will be adopted as an ESA mission either in spring or summer of next year. That's a whole different story, but it's not going to fly till the mid-2030s, so plenty of time to get me back to talk about that. So in this whistle-stop tour, I hope that I've convinced you that although it's a relatively young field, that it does have a very bright future. Thank you very much.
Thank you very much, Martin. There's a lot of detail there. I'm sorry we can't spend more time on it than we have. Any quick questions? Gentleman over here.
Japan is seismically active.
Mm-hmm.
Is that a good place to build a detector?
It's an excellent question. To be honest, the Pacific Northwest is rather seismically active too. When you're trying to mitigate, you know, effects that could swamp signals that are a millionth the width of a hair, frankly, seismic activity doesn't matter that much. I mean, it clearly does if there's a major earthquake and your lab shuts down, but you need to be able to mitigate and sort of filter out a lot of low-level seismic activity anyway. Even in Pisa, you know, you've got to do that too. So long story short, the principal driver was that this is an underground facility that was already in existence. The Kamiokande mine, where the neutrino experiment is where Kagra is sited. So having a lot of that infrastructure in place was the main reason why that site was chosen in Japan.
There was a question, yes, right at the back there. Martin.
Yes, so as you showed a picture there, that neutron stars have quite a defined structure to them. So what happens after a neutron star merger? Is that structure reassert itself after a bit of churning? Could you get a black hole after that?
Well, we think almost certainly you do. The neutron star merger that occurred in 2017, based on our estimate from the gravitational-wave signal of what the final mass was, and based on our theory of how massive a neutron star is allowed to be, we think that that remnant was almost certainly a black hole. But our ability to interrogate that will improve with these future detectors. We'll have very, very high signal-to-noise observations, not just of the in-spiral before the merger, but the ring down after the merger. And that will help us to really work out, well, does it become a black hole? If it becomes a neutron star, then what you would see is different harmonic structure in the signal than if it is just a black hole. And that ties in with a lot of heavy-duty theory from people like Stephen Hawking and others that basically say, you know, you can't learn that much about a black hole other than its mass, whereas if it is a neutron star, if neutron stars were allowed to be more massive than we think they are, then it would have an effect on the structure of the gravitational wave signal as well. You could do kind of neutron star seismology in that respect. So all of these, you know, we just have to wait a few more years, but these are the kinds of astrophysical questions that we hope the current and then next generation of detectors will let us answer. Thank you. Great question.
Well, I'm afraid we have to get on now. It's time for the tea break. Thank you very much for coming all the way from Scotland.
Not at all.
And you have to rush off now, don't you?
No. Well, my colleague Lyndsay also came all the way from Scotland, so I'll certainly be around for that. I'm sorry I can't stay for the reception at the very end, but I'll be delighted to chat to people during the tea break if anyone has any further questions.
Thank you. Thank you, Martin. And now refreshments should be served outside, and we will start again at 4:05. Welcome back to the second half of our Christmas meeting. Professor Lyndsay Fletcher also has a connection with Glasgow. She did her undergraduate and PhD degrees at the University of Glasgow. Then she moved to the Netherlands and the United States to carry out postdoctoral research in solar physics. And she returned to Glasgow in 2000 and is still there. But she's also a professor at the University of Oslo. She researches solar flares using imaging and spectroscopic methods and simulations to try and understand the sun's chromosphere and solar flares. She's been Senior Secretary of the Royal Astronomical Society and President of the IOU's Commission on Solar Activity, and she's a Fellow of the Royal Society of Edinburgh. And she has received awards for her work on improving equality and diversity in physics. Perhaps you can give us some hints about improving diversity in the BAA afterwards. Right, and she is here today to talk about exploring the solar atmosphere, a journey through the sun's spectrum. Professor Lyndsay Fletcher.
Thank you very much, David, and thank you everybody for coming. So yes, I'm going to be talking about the sun's atmosphere and the sun spectrum, and unlike Martin, who's talking about a very new science, a very new part of astronomy, we've been doing solar physics for a long time. Not as well as this is recent, but you know, since, well, arguably since the first person started to look at the sun and plot its trajectory through the sky, but certainly since Galileo started to draw sunspots. Actually, probably it wasn't Galileo who started, it was probably an Englishman called Thomas Harriot, but nobody talks about him because he wasn't very good at advertising his work. However, here are some views of the sun. In fact, just quite recently, these are views from sort of the middle of November to just 3 or 4 days ago, when the sun was through a very active phase. There was lots of flares and coronal mass ejections, which led to northern lights, which people might have seen. I don't know if anybody saw the recent northern lights at all. No, I was in Oslo, but oh, you did? Lucky you. I was in Oslo and managed to miss them both times. I was eating both times. This is not very good. But anyway, these are movies of the sun taken from space in two different filters. The kind of filters you put in front of your, ordinary telescope, but just a bit more expensive and put on a satellite, so that we can see the sun. The red one is looking at a particular spectral emission line of helium, and the yellow one is looking at a spectral line of iron. And so we see two different temperatures. The red one shows us the chromosphere of the sun, and the yellow one shows us the corona of the sun. And they are false colour images. The colours don't mean anything, they just look nice. Most of what we'll see is false colour images. So the images are very, very powerful. We can see dynamics. This is speeded up enormously, of course. The solar rotation takes about 25 days, and this is, a couple of minutes, and it's halfway around. We can see dynamics, we can see different features, we can see lots and lots of detail on the surface of the sun. And we can watch flares in progress. This is my area, of course. We've taken 3 separate images and stacked them one on top of the other and done a bit of colour blending, just like they do when they're making Hubble Space Telescope images or other images, to bring out the detail. And what we're looking at here is the graceful rise of what's called the magnetic flux rope, turning into a coronal mass ejection. And at its base is some brightening, which constitutes a solar flare, which is what I do. So we've got lots and lots of fantastic images. And we can compare them, and we can try and understand the relationships between different bits of the sun measured in different parts of the electromagnetic spectrum. So thank you, Martin, who introduced the idea of the electromagnetic spectrum. The electromagnetic spectrum is electromagnetic waves, broadly speaking light waves, which extend from the gamma ray regime up to the radio regime. And what we're seeing in that beautiful composite image behind us, basically the orangey bit is the visible, that's the surface of the sun, the photosphere, and then the kind of funny green and sort of muddy green and muddy pink bit, that's ultraviolet radiation, which comes from the chromosphere of the sun, and then basically everything else is somewhere in the sort of low energy X-rays part of the sun. And so by putting all these images together, we can understand some aspects of the physics of the outer part of the sun. Let's just remind ourselves what we're seeing when we look at the sun. If any of you have, and I know one gentleman over there has a solar telescope, and probably some of you have more, parts of the sun's atmosphere are accessible to you. Most familiar is the, let's see if I can make this thing work. This is going to work. Oh, yes, look at that. Oh, brilliant. Right. Most familiar is the photosphere, the visible surface of the sun, where we see sunspots, and we broadly call this white light, the white light surface of the sun. This is the part of the sun which is visible to our eyes, and we can see things like, well, the spots here. We can see it's a bit darker at the edge than it is at the center, and that's called limb brightening, and that actually tells us something about the way that energy is transported through the atmosphere of the sun. And then on the other side here is the chromosphere, and this is an image made with a filter which is tuned around the H-alpha line of hydrogen. This is a very strong spectral emission line from the most common element in the sun, which is hydrogen. And we're looking at things which are about 10,000 degrees centigrade here, whereas in the photosphere it's about 5,500 degrees centigrade. And so we can see differences, clear differences, when we look in different parts of the spectrum. And the chromosphere is a kind of a thin shell on top of the photosphere. Let's just, and these kinds of images can readily be made from the ground with small small ground-based telescopes, because the radiation comes through our atmosphere. If we want to look at the corona, well, if we're lucky enough, we can see it during an eclipse for about 7 minutes, but otherwise we have to go into space. And so I'm going to step through an animation of different layers of the corona, but starting with just the photosphere here. This is an image from, again, the Solar Dynamics Observatory. We see sunspots and so on. This is from a little while ago. And we can step through wavelength, going into the ultraviolet. Again, false color images. There's a little solar flare going off here. So we're stepping through the chromosphere, getting up to temperatures of around 100,000 degrees centigrade here. And then where the spot was, you can see that there are these bright regions called active regions. And then just sliding on up into about 600,000 degrees centigrade gas, edging towards the million here. So you'll notice I'm giving these numbers. I'm saying I know what the temperature of these parts of the solar atmosphere are, and I could also tell you what the density is and how fast it's going. And how do I know that? Why do you believe what I say? Well, images are fantastic. Images are what brings people into astronomy. Images are made in a familiar way, and so this is actually the instrument itself. This is the Solar Dynamics Observatory, and it's got a suite of 4 telescopes at the top here. And those telescopes are just little Cassegrain telescopes. Each of them actually images in 2 wavelengths. You can see the filters at the bottom here, actually 2, and this one's got 3 here. But they're just little ordinary telescopes, and they've got fancy filters in front of them to select different wavelength ranges. And they are just like, you know, sunglasses, if you like. You know, you look through the pink glasses and you see the pink things, and you look through the blue glasses and you see the blue things, broadly speaking. Of course, these filters are much more expensive than these glasses that you buy off Amazon for £5.50. They cost hundreds of thousands, if not millions of dollars to tune them, so that they select as narrow a part of the spectrum as possible, that they work in space, and also that they work at these very, very short wavelengths. This is going down to 131, actually 94 angstroms. The radiation that we see with our eyes is about 5,000 angstroms, so we're way, way out in the extreme ultraviolet part of the spectrum. That's really hard to make things that work there. So, imaging is one way of looking at the sun, but what I'm going to really talk about is spectroscopy. Spectroscopy is what you discover, what you learn when you break light up into its constituent colours, which we have done in a way with these filters by blocking out everything else, but this is something different. So we're familiar with a prism. You shine sunlight onto a prism and it splits into its rainbow colours. Very beautiful. There are other technologies. This is called a transmission grating, which is basically like a very thin sheet of plastic with many, many lines ruled on it. And the like thousands per centimetres, or actually thousands per millimetre, what am I talking about? And the light interacts with that in such a way that it gets, again, split out into its colours. And it's much lighter. It's not made of glass. In this case, the professional ones are made of glass. Actually, I've got a bunch of them in my bag. I meant to hand them out. I'll do it after if anybody wants. So the light comes through and is split out. Actually, this is split out. Some of it goes straight through. Some of it is transmitted. But here we get the rainbow here and here, and also what's called second order here. So we get second order down here. And you can get glasses that do this as well. If you want to go to a rave, you can buy them and everything. So this is spectroscopy, splitting up the light into its different colours. And this was first done by Joseph von Fraunhofer in about I'm not sure, maybe Martin will remember, 1830-something probably. And he looked at the spectrum of the sun. And it's maybe a bit of a faint drawing here, but along the top, the curve, you basically see the total brightness that he measured. And it's got this characteristic shape called a black body shape. But also what you noticed is that there's lots and lots of lines, lots and lots of gaps in the spectrum. And the strongest of these are now called the Fraunhofer lines. Some of these lines come from the way that light interacts and is absorbed when it comes through the Earth's atmosphere, but some of them come from the sun. So this is what's called an absorption spectrum. And how do we make an absorption spectrum? Actually, my animation's going to be a bit funny here, never mind. So here we have the sun. That yellow circle was supposed to be superposed on the white circle, but something has slipped, I don't know. So here's the sun, and here is what we call a slit. This is a small aperture. You have to select a little part of the sun, to study, and a prism. And so light comes from the sun, goes through the slit, arrives at the prism, and is split into a spectrum. And if you have a hot object, like the sun, which is surrounded by cooler material, like its photosphere, which is a little bit cooler than the interior of the sun, then you get an absorption line spectrum. Some of that radiation gets sucked out, if you like. And if you have a hot, tenuous material, like the corona of the sun here, if we take that light and split it up through a prism, actually a diffraction grating, then you get an emission line spectrum. And the two are kind of complementary, in fact. You get two different kinds of spectra. And let's just ask ourselves quickly, where do the lines come from? So here's an atom. In fact, this is carbon. I've drawn a carbon atom because it's got 6 protons and 6 neutrons in the middle, and it's got 6 electrons zooming around it. So, first of all, here comes a photon. It interacts with that electron, kicks the electron into a higher orbit, takes the energy from the photon, gives it to the electron, and the photon disappears. The photon has been absorbed by the atom at a precise energy. And so radiation at a precise energy or wavelength is absorbed and a dark line appears. And every element gives a different set of dark lines. In fact, every element, in something I'll come on to later, in different stages of ionization gives different lines. But the reverse can happen. So on the other side there, we have, again, am I missing? No, I thought I'm missing an electron there, but if you see in the middle here, we've only got one. There should be 2 electrons in the inner shell here. There's only 1 in the inner shell. We've got 5 in the outer shell. We don't like that. Unstable situation. An electron transitions down and emits a photon. And so in that case, you get radiation at a precise energy or wavelength which is emitted, and a bright line appears. And so from the same atom, under different conditions, you can get radiation absorbed or emitted, and it's exactly the same wavelength. Now, we can do a modern Fraunhofer and look at the whole solar spectrum. So this is, many sections of the spectrum that have all been kind of glued together and then stacked vertically. And this is what we might call the sun's chemical barcode. There's many absorption lines in there, and they haven't all been named because there are literally hundreds of thousands of them. But the strong ones, we can see this, see the hydrogen line, that's actually H alpha. And then these two guys, sodium D lines in old-fashioned street lamps, which are rapidly being replaced, which astronomers hate, of course, because you can control the sodium D lines by putting in a filter that blocks it out. But these sodium D lines are emitted by the gas in the old-fashioned yellow street lamps, but they're absorbed here in the sun's atmosphere. And then we've got some magnesium, some iron, some hydrogen, more hydrogen, etc. But you can see there's loads of spectral lines there. And so we can identify the elements which are present in the sun and also, of course, by extension, in stars. But there's much more than just the chemistry, if you like, or the element abundance. If we look carefully at these lines we see, some are hard to see. They're faint. Some are very obvious. They're strong. Some lines are very narrow. Some are very broad. And some actually have a different wavelength from the values you would calculate based on atomic physics, from their theoretical values. And all of these properties of the spectral lines encode the physical condition of the emitting material, by which I mean its temperature, its density, its speed, and even its magnetic field. And now we are doing astrophysics, not just astronomy, astrophysics. So I'm going to be showing you some spectra and spectral images. So I just want to explain a little bit about what we're seeing, because sometimes it can be a wee bit hard to wrap your head around. We make a spectrum by looking at a small patch of an object. You can make a little square aperture and create a spectrum from that. Or more normally, we make a slit. Okay, so the white line in both of these images is the spectrometer slit, or a spectrograph slit. And the light goes through that slit, meets a prism or dispersing element, gets spread out into the spectrum like this. So that would be an absorption line spectrum. And so if we look along the slit, it's corresponding to along each of these spectral lines. And here's an emission line spectrum, again with a slit, and it gets dispersed, what we talk about, the dispersion of the radiation. Wavelength is along this direction, and so a brighter part under the slit here corresponds to a brighter section here. So we have an absorption line spectrum and an emission line spectrum. This is made from Earth, this is made from space because it's in the extreme ultraviolet. We've got wavelengths of 195, 200, 205 angstroms. Okay, so this is the basic observation is a spectrum which is a slice of the sun dispersed in wavelength. Now we have to make an image out of this, a picture, a two-dimensional picture out of this. So this is how it's done. Again, here is our emission line spectrum. We choose a spectral line that we like. This is a nice line. This is from iron, which is 9 times ionized. It's 195 angstroms. It's a nice, strong line. And we cut that out and put it there. And then we move the slit to another location. We make another image. We cut out the line and we put it there. And we do it again, and we do it again, and we do it again. And gradually we build up an image as the slit moves across the surface of the sun, or the telescope slightly changes its pointing so that the slit moves across the surface of the sun. And this is called rastering. This is called a raster. And when we do that, we can look at the solar atmosphere in many different spectral lines. And so here's an example of a series of lines from the element iron. And each of these numbers after it, there's iron 8, iron 10, iron 11, iron 12. This tells us how many electrons that iron atom still has. And that corresponds to different temperatures, 500,000 centigrade, 1.1 million, etc., up to about 2.8 million centigrade. So by splitting our spectrum up and making these images, we can look in a very great detail at the temperature evolution, if you like, the temperature, how things look at different temperatures in the corona. And the reason for this is that if you have a low temperature situation, here we have a neutral atom. Again, we've got a carbon atom and it's got 6 electrons around it. Now, if the temperature gets a bit higher, then some of these electrons start to basically fly off or get hit off by other particles or by photons. And so this becomes ionized. This is twice ionized. And now this poor soul has only got 3 electrons left. It's 3 times ionized. So every time the temperature increases, you start to lose electrons. And when you do that, each ionization stage, we call this is neutral, and then this is the second ionization stage, and the third ionization stage emits a different set of wavelengths. You can look at a spectrum and you say, this one comes from iron 10, this one comes from iron 6, for example. And that corresponds to a fairly precise temperature. So you can learn the temperature that way. Density is a wee bit more tricky. Here's our atom again. Some spectral lines are formed after collisions with electrons. So an electron comes, let's go back. An electron comes flying in, knocks an electron into another orbit, and a photon is emitted. More electrons per cubic meter, that means a higher density. More collisions, stronger emission. And so that means that if you compare the strengths of 2 spectral lines, one which involves collisions and one which does not depend so strongly on collisions, means that the value of the density can be calculated. So we've got temperature, we've got density, then we can start talking about pressure and all kinds of physicsy sounding things like that, energy, etc. We can start to put physics numbers on pictures, basically. And so that has been done. Here's an image of the sun. In fact, you can see, if you look closely, you can see that there are actually lots of little slit images here. It's kind of broken up, and there's a missing one up there, for example. There's a missing one there. So there's an image of the sun made in iron 9, and there's the density, a density map of the same features. And so we can see there's high density in these active regions, and there's low density in regions called coronal holes, for example, where the solar wind is just escaping out into space. So temperature, density. What about speed? The speed is actually quite an easy one. It uses the Doppler effect. So if a source is moving, there's a source moving to, that's the right, isn't it? Moving to the right, and if you like, all of the light waves get crushed up. Their frequency or the wavelength decreases. Let me run that again. And that means that, yes, I've got this the right way. I've got this the right way around. This is the spectrum which you would see at rest. Decreased wavelength means that the gas is moving, sorry, beg your pardon, the emitting object is moving towards us, and so everything is moved a little bit to, I think I have got this the wrong way around. Sorry, I've got it the wrong way around, haven't I? Yes, yeah, because yes, this should be moving more to the blue if it's moving towards us. Okay, I've got that the wrong way around, I'm sorry. You get the basic principle. You get the basic principle. Okay, so, sorry, I just want to run this again, but I've managed to mess up. Okay. Yeah, okay, final. Anyway, you can measure the offset of the spectral line from its rest position, and that way you can then work out how fast things are flowing. And so again, here's a picture of an active region where we see the brightness. This is probably, again, about 1 million degrees. I think this is probably iron 9 or iron 10 again. And by measuring the Doppler shift at each location here, we can see that on the very edges of this magnetic active region, as it's called, under here would be sunspots, a pair of sunspots. And the very edge of this active region, the material is flowing out towards us, moving it up to about 50 kilometers per second, which is not actually very fast for solar flows, but we think that's the beginning of the solar wind. Some of what the so-called slow solar wind is leaking out of the edge of the active region towards us. And in a location like this, like this, we can see some kind of arches where there's material which is moving up on one side and moving down on the other side. And so we think that there is a flow along these field lines. So we can start then to talk about kinetic energy. We can start to understand the way that the gas from the surface of the sun makes it out into the wider corona and the wider heliosphere, and ultimately towards us at Earth. And then the final diagnostic, if you like, is of magnetic field, and this is called Zeeman splitting. And so here is an image, rather an old image of a sunspot, and down the middle here is the location of the spectrometer slit. And here's a little chunk of spectrum, and what you can see here is that the spectral line, it starts off at the top as a single line, it gets a bit broader, and then it splits out, in fact, into 3 lines. And it does that in the presence of the strong magnetic field in the center of the sunspot. And so that's the way that Zeeman was able to identify that there were strong magnetic fields in sunspots. And that Zeeman splitting, again, it's a spectroscopic technique which is now being used in great detail to look at the surface of the sun using a new facility called the Daniel K. Inouye Solar Telescope. Okay, and so this is a filtergram image of the quiet sun. There's all kinds of beautiful detail there. There's all kinds of what's called fibril structure and bright points all along here. These are outlining the edges of huge convection cells. You might be able to just see a sort of cellular structure here. And you can make a magnetogram of the same area, and we can see that the magnetic field here is strong. So brown means the field pointing towards us, and blue means the field pointing away from us. So we can see that the field is strong around the edges of these cells. It's actually relatively straightforward to do this at the surface of the sun, but doing it in the atmosphere of the sun is somewhat more difficult. There's a beautiful picture of the corona seen in white light during an eclipse, made by some colleagues in Hawaii and in the Czech Republic. And so we have a white light corona here. And if any of you go and see the eclipse next year in the States, you won't see anything like this at all, but it will still be mind-blowing. Here's the same image, but now with what's called the coronal green lines and red lines superimposed on them. These are lines emitted by the element iron. And there's an interesting story related to that, because for a long time, nobody could identify from all the atomic physics they knew what those spectral lines were, what the green and the red line were. The reason that they were having trouble identifying them was because they assumed that the corona of the sun was cold. Big mistake. The corona of the sun is hot. The corona of the sun is about 1 million degrees or more. And it's only when you admit that possibility that you can identify those spectral lines, because those spectral lines should not be emitted by cold plasma, but they are emitted by very highly ionized iron. So there's a sort of a story there about, just always confronting your expectations, sometimes in the most radical way. And the radical way was to say, well, the corona must be about 1 million degrees. That's the only explanation. There's a Sherlock Holmes phrase about this. When you've eliminated all other possibilities, then the most unlikely one must be the truth. And that was the truth. So the Zeeman splitting can also be used in these spectral lines, in the green lines and the red lines, the green line and the red lines, to work out the corona's magnetic field. However, it's going to take a long time to do. You see this little box on it, on the corona? That is the field of view of a new coronagraphic instrument, which is meant to do that. And it takes a couple of hours to cover that field of view and get the spectrum from each point. So it's going to take a while before we can map the magnetic field in the whole corona. Okay. I get to show you the only picture I have of me at a telescope, which I actually use. This is the Daniel K. Inouye Solar Telescope, and that's the telescope which has got this tiny little field of view, but is nonetheless going to be measuring the solar magnetic field in its corona. And so this started taking science data just kind of in the middle of the pandemic, so results have been a little bit slow coming, but this is our favorite new thing in solar physics. In terms of space, in terms of astronomical telescopes, it's not enormous. This mirror, which I'm posing in front of, this is the main mirror here. It's about 4 meters across, and nobody builds 4-meter telescopes for nighttime astronomy anymore. It's all like 30-meter telescopes. But for solar astronomy, it's pretty good. However, it's actually not good enough, because by the time you've taken all the light from a small portion of the sun and split it up into all its component wavelengths, and realized that things change really fast on the sun, timescales of seconds. So you want to make exposures that just like hammer away much faster than a second. You don't actually have all that much light left to play with, to do your analysis with. Plus, this baby has got about 11 mirrors before you get to any science instruments. And so every time you put a mirror in the light path, you lose some of your photons. 11 mirrors to take the light from this thing down to the first science instrument. However, we're going to be doing great spectroscopy using the Daniel K. Inouye Solar Telescope. Okay, right. I've just actually got a couple more slides, and hopefully we can have a bit of a discussion. All of the pictures that I've showed have really been of, or the spectra I've showed have really been of fairly slow-moving / stationary things. What happens when we have fast-changing events? Now, I'm going to show you a couple of what's called, well, in one case a raster, but the other a sit and stare of a flare. And this were observations made with the IRIS spacecraft, the Interface Region Imaging Spectrograph, which has been flying for a few years and is a really powerful instrument looking at spectroscopy in the ultraviolet part of the spectrum. So we're looking at a small patch of the solar surface, And inside this box, I hope you'll be able to see a slit moving from left to right. Quickly, quickly, quickly. And so this is what we call a small raster. Now remember, in the raster image that I showed you at the beginning, each new slit position, you add a little bit to an image, and so you can build up a picture of the sun at a very precise wavelength. And so it goes backwards and forwards, returning to the same place after about a minute or so, which is great until something dynamic like that happens, like a flare, which is, of course, my baby. I really enjoy studying solar flares. Flares happen, and many other energetic events happen on the sun over timescales of minutes or less. And so the slit never goes back to the same place and finds the plasma in the same condition, or finds the gas in the same condition. So how do you get a good picture of what's happening with a good enough time base that you can really track the physics of what's going on? The other thing is the return is about a minute in this small raster, and so in a minute a lot has changed. So it's very hard to make a physical connection between what the sun was like at the time when the slit was at the right-hand side and then a minute later when it returns to the right-hand side. So you can, to some extent, get around this by just having the spectrometer slit sitting at the same place all the time. So you've only got information from along this line. In that case, you can run very much faster. You can, oops, hang on. Can I make that go? Can I make it go? Yes. Yes. You can run very much faster, but again, you're only taking a little tiny slice of this whole picture, and something like that happens. And now we have the image in the background. I should explain, this is a clever piece of optics engineering, where you build in what's called a slit jaw camera. And so basically on the plate where the slit is, the spectrometer slit is, you set up some fancy optics to reflect the light to a detector, so you can always see exactly where on the surface of the sun this slit is. That's a slit jaw camera. So the background is a slit jaw camera image, and the black line is where the spectrometer slit would be. So we can see that there's a lot of dramatic stuff going on there. But we can only measure in this one narrow region. And so we just lose so much information. You can make approximations, you can make guesses at what's happening in the condition of the plasma, not on the slit, but we only really have a few locations where we can see in great detail what the temperature, the density, the velocity, the magnetic field is. All these things we really want to know. So we're a bit stuck. Or we were a bit stuck until a new design appeared for a new instrument, which is called MUSE, the Multi-Slit Solar Explorer, it's called, and it's been built by some of my colleagues and indeed my friends in the United States at Lockheed Martin Solar and Astrophysics Lab, and I'm very proud to be what's called a science co-investigator on this mission. And instead of one spectrometer slit, there's going to be 37, all working together in concert. And so what this little movie is going to show is a calculation of what MUSE will be able to see compared to what existing spectrometers will be able to see. And these are calculations based on very advanced, what's called numerical simulations, computations of how the temperature, density, velocity of solar gas behaves during an eruption. And so if I just run this, then the furthest left panel is the calculation of the eruption, showing its brightness, and the blue and red are showing the speeds, the Doppler shift towards us in blue and away from us in red. And so that's the ground truth, if you like. And you can simulate what MUSE is going to be able to do, and then that's the second from the left. And so you can see that with the multiple slits all operating in concert, it's going to do a fairly good job at capturing the red shifts, the blue shifts, and the intensity as this very dramatic thing evolves over a large field of view. But if we compare that to existing spectrometers, the third panel is a comparison with another spectrometer which is being built called the EUVST, the EUV Extreme Ultraviolet Solar Telescope. And so it will manage to go to raster across the whole image and capture a sort of average of its evolution. But then the furthest on the right is our current best, the Extreme Ultraviolet Imaging Spectrograph, and it doesn't even get right the way across. So I'm very excited about MUSE. MUSE is going to launch in 2027, and I think it is going to revolutionise our ability to use spectroscopy on very rapidly evolving events like solar flares. Okay, that's me at the end. In fact, I would like to thank you very much for your attention, and I'm very happy to answer any questions before Martin and I have to run off and get the train. Thank you.
Thank you, Lyndsay, very much. I was just thinking somebody must be employed to come up with those the logos. But that was a very clever one with the lyre shape, and the strings are made out of the slices of the spectrum.
Yeah, very nice.
Yes. Or maybe you do that in your spare
No,
time.
I don't have the skill to do that, no.
Questions? Over here, this lady.
Yes, hello. I just wonder, the new instrument you just showed last, yes, is this a spectrograph as well?
It is also a spectrograph,
and,
yes.
Do they put it at the telescope which observes the sun in space?
Yes, it's a space-based spectrograph as well, yes.
And they put it on there, on this?
Yes, it is.
That's what I thought.
Yes, yes. So it's quite risky, but, you know, it's quite a delicate piece of machinery. With all these, it's got multiple slits moving across, different mirrors inside, and so it has to be tested to make sure it's going to survive launch and so on. Sometimes they don't survive the tests. But yeah, so it's a tricky thing to put up there in space. It's much easier to put fancy instrumentation on the ground where you can go in and twiddle it if it goes wrong. Once it's in space, there's no going back, really.
Over here.
Yes, hello. I've really enjoyed your talk, and I was wondering, you talk about the transmitted and the emitted lines, and I'm sure they're both very useful type of thing for your science. But which one would you say there's more? Some of them are more useful in terms of. Would you say the emitting is more useful for your sort of work?
So, yeah, good question. So for my kind of, well, actually my kind of work, I now use both of it, but it really depends, I think, on the part of the atmosphere that you're looking at. If you're looking at the outer tenuous atmosphere, the corona, then all of the light you see is these emission line spectra, the mostly dark but some bright line spectra. When you look at the lower atmosphere, the photosphere, then it's all the absorption line spectra. So it really depends what bit of the sun you're looking at. Of course, what we want to do is try and put it all together and learn something about the behaviour of a certain part of the atmosphere, going right from the photosphere up into the corona and beyond to get the whole picture of what we call mass, energy and momentum transport from the surface of the sun out into the heliosphere. That's the big picture.
Thank you.
So I'd assume that you could calculate the magnetic, therefore, like it's a magnetic field generated by like the movement of like the flares. Is that the same as what like you see in the Zeeman effect, or is that a different magnetic field?
So the Zeeman effect will show you magnetic field, allow you to measure magnetic field wherever you look for it. And so if there is magnetic field changes during a flare, we don't see really anything that looks like magnetic field being generated, but being changed, certainly. Then you will see that through the Zeeman effect, and in fact we do. We see it. We look at the photosphere of the sun, and we see that when a flare happens, the corona changes, but the photosphere also changes as well. So these are really active questions that people are looking at just now.
Just time for one more.
Yeah, I'm going to have to run off, I think.
Yeah, sorry, can you just clarify, when you talk about hydrogen, are you talking about monatomic hydrogen or molecular hydrogen?
Ah, very interesting. Most of so our friend H alpha up there is monatomic hydrogen. However, coincidentally, my postdoc, Dr. Sargam Muli, and myself have just discovered molecular hydrogen in solar flares, which is quite interesting because solar flares are hot and you shouldn't get a lot of molecular hydrogen there, but it's there. So there's a whole area of molecular spectroscopy in the sun, which is starting to just open up now.
Right, well, thank you very much, Lyndsay. I know you and Martin have to rush off back to the north, where you don't get much sun.
No.
So thank you very much.
Thank you very much.
Next we have John Chuter, who is one of the BAA's honorary archivists, who's going to talk to us for a few minutes about the project to digitise the archives.
10 minutes. Yes, Richard McKim and I are co-archivists of the BAA. I have been for a number of years now. And Richard and I would consider the BAA archives to be the physical archives that are stored at 2 stores at Bedford, and now all significant archives and retained book library at Max Communications. And one of the things I've been wanting members to be able to do for quite a number of years, and I've been a member for nearly 40 years, but I've only been in the higher echelons the last is for ordinary members to actually know what the archives, the physical archives, have got in them, and also how they might be able to access them. Sorry, I'll just go and find my particular. The good news for you is that mine is only one slide. Doesn't need to be anything else. There we go. Okay, I was doing it like that. Oh, what are you seeing? Oh, there we go. Right, okay. So now, what I had hoped was that the October or December journal would have landed on your doormats, is the phrase that the people in BAA use, or appeared on the website, because my archive piece this month, this issue, is actually going into a bit of detail about what this archive website is meant to be. The trustees very kindly allowed a sum of money towards the end. In fact, it was just, 2 or 3 months into this year to begin funding the development of a website. And we chose Max Communications because they actually professionally do this kind of thing. And as well as developing the website, they've scanned quite a lot of the significant things that are housed there. And you might be able to read them there. All the minute books, this is what cracked the door open, by the way, to me getting money for all of this, because it was decided as a charity, with minutes going back to 1890, that members should be able to read them. And so they have all been scanned, and they are actually now on this website when you're able to get in there and have a look at it. But equally, within the archives, you have some very interesting notebooks of old past members. Roland Clarkson, I know Bill over there has got a great interest in. We've got his complete set of notebooks in the archive, about that high, very fragile. They've all been scanned, as have the notebooks of Major Molesworth. Now, I had 1 or 2 of his items at last year's Winchester weekend, and I know that certain people in the audience had a look at these things and thought they were rather amazing. Well, the ones we have been scanned, and they are now on this website. There's other scans that have been done. You can read it in more detail. There's a little bit more detail there. I just wanted to show you what the actual website is. Hopefully this works. Should go off. Oh, there it is. It's not on here, mind. So I just come out of that. I'm going to have to fiddle around now. Where's it gone, the web on here? Okay, is there a pointer somewhere? How can I find it on the screen here? Oh, here it is. Get that to come up. That's not coming up. Can't see a pointer. Where's it gone? Could you get it up there and on here so I can actually see what I'm doing? I don't do this particular thing very often. Oh, there it is, but I can't see it on there. Right, I'll carry on. What you can see is the front page of the website, and it's all you'll be able to see as it's there we go. Okay, good stuff. Right, now if you scroll down, there's some wording I've put into here, created a logo and so on. You'll notice a login button there, and I've put some information about the BAA website. Now, crucially, Richard has spent a long time creating the catalogue of the archives as they exist in these storage locations, and this will be freely downloadable. It's a very, very long Word document with PDF now, where Richard's gone into a great amount of detail about all the things we have physically got, own, have, maps, books, notebooks, globes, anything and everything you can possibly think of, old Walter Goodacre medals and so on. I've spoken about these in my pieces over the issues that we have. So that's freely downloadable if you want to have a look at it. And at the moment, the good news and bad news is that if you try to do anything else without a login, you can't. All right? You will need to have a login. Now, this is a work in progress. It's actively being worked on. I've noticed, for instance, that font sizes are slightly different and so on, and Richard put me right on what this actual picture was here, which is actually a room of the BAA office located in the home of a former Assistant Secretary, Lydia Brown, of which we have a medal now, in Hounslow West about 1970. But if you get a login, and I don't know whether mine will appear, of course it won't, if I can just, I'm not on there. Okay, let's just put myself in. Now, because I have sort of an admin access, they'll be a bit more visible on mine than will be on yours, or whoever goes to have a look. And I'll put get the password in. It's not visible. Now, we both worked at a school, and my wife didn't realise a real troublemaker was looking at her password. It was on view one day. She said, right, okay. Now, if you log in, I should say never to that. Now I'm logged in, I can actually go to something called archival descriptions, and you'll find that there are two things we've got at the moment. We've got BAA Office and Administrative Records, and within there you have all the minutes. It says draft because it hasn't actually been properly put in yet, all the way from 1890 to 2000, and if you scroll down, you'll find you can actually have a look at any one of these that you wish. They are rather large PDFs, so I won't do those ones at the moment. But I'll just go back to...
John, have the PDFs been turned into searchable documents?
If they're typed, yes. But if they're not, we need to think they do. Well, there's a bit of an exercise doing that. We need to go into that one. But any typed ones will be, yes. Right, if we go back to archive. How do I do that? Archival descriptions. Right, the other one, which is more interesting, is individual astronomers, because in here we've got most of the things that Max have scanned for us. If you go, for instance, to Molesworth, you will actually see the various things that Molesworth has done that we own or we have in our archives. And as some of the people over there saw last year at Winchester, we do have this rather amazing moon observations one that he did. I can put the right one. Where's it gone?
The top there.
Up the top. That's this one here. This is an amazing document. If you get it loaded up, if you can get it loaded up. Not on the right one, I don't think. Where are we? Oh, this go on. You can see what I mean. They're all there, and you can load that up, and then you can have a look through it, wherever it happens to be. This is the right one. this is Major Molesworth all those years ago in Sri Lanka, and he did this amazing piece of work, which even Stuart, who does this at Max for us, has become interested in himself when he actually looked at this. He thought it was just amazing if you actually look at the quality of the work this chap managed to do all those years ago. So that's one of the things we've got. Oh, I'm not sure what I'm doing here now. Go back. We've got other things. We've got Clarkson, Bill, as you might see now. Here we've got Roland Clarkson. We've got all of his notebooks on here on a carousel. If you show all of them. It's easy when I'm at home doing this. So here we have some quite interesting stuff here. The first thing I ever saw when I became archivist was the Clarkson notebook he did on the solar eclipse of 1927. So that I found quite a very interesting thing. But the other thing we do have, these are all from Roland Clarkson, corresponded with Richard Baum quite a lot, although Richard Baum has a lot of his letters. And there's a whole lot of them here, which you can go and have a look at. Very interesting. And we've made a start. There's some other things. We haven't got these available for you to see at the moment, but as James over there will know, we do have the complete set of 30 notebooks of Alan Heath. In fact, not notebooks, they're huge, great folders. There's 3 great, huge boxes in the Bedford store, and I managed to get one of those scanned, just to find out how much it would cost to do all 30 of them. So the reason I'm standing here today for 10 minutes is to persuade the trustees that we now need to spend more money scanning some of this stuff so we can put it onto this website with a lot more other stuff. So that's the reason I'm standing here, and it's the only reason I'm standing here. So there we are. Have I got my 10 minutes?
Yes, I think that's enough of that, John. Thank you very much. This will be a great resource for future historians of astronomy. Thanks, John. You're doing a tremendous job. Now we come on to Nick James, who has the sky notes, what's been going on in the sky recently, observations submitted, and some things to look forward to. Thank you very much.
Thank you, David.
Oh, sorry about that.
That's all right.
You haven't got a login, so you can't get in.
Yeah, no worries.
Yes.
Aha, right, yes. So, welcome to the Christmas Sky Notes. And it's a shame Professor Fletcher isn't here because I've got some fantastic pictures of the aurora, which she didn't manage to see, and which obviously not many people in this room managed to see either. But this thing, and I'll talk a little bit about it later, is this mysterious thing called STEVE, which is a backronym now. I think it supposedly stands for something thermal emission of something, but something like that. But it was originally named Steve after a kind of cartoon book character. But it's something that nobody ever mentioned up until a few years ago, and suddenly everybody's seeing it. And there was an incredibly good example of it at this recent aurora on November the 5th. It's not a firework. It is a real thing. So I've got a laser pointer. I'm not sure I can cope with doing it on the screen. Does that? No, it doesn't. It just points a laser at the screen. Hooray. Right, so yes, the sun's been quite active recently, but not so active at the moment. If you could actually see the sun, and I haven't seen it from Chelmsford for about a week, you would see that it's not got very many sunspots on it. But we've had some nice images submitted of sunspots. This one from Graham Winstanley on November the 25th, showing a good selection of sunspots. So this is a white light image of the photosphere. And then we have this one taken with a Coronado PST. So this is hydrogen alpha, showing the detail you can see in that wave band with some nice prominences and flares and other features on the sun too. So the sun is coming up to maximum. I think maximum is due sometime next year, or 25, I think, something like that. It's a bit ill-defined, but it's certainly coming up to maximum. And as a consequence, we've certainly had a lot more auroral activity. So here is this fantastic picture by Steve Brand from North Yorkshire showing this Steve event. So this isn't the same thing as an aurora, even though it takes place at the same time. And this was actually a single kind of bright beam crossing over the whole sky. So a number of people were lucky enough to see this. So this is Steve's picture from North Yorkshire. And we also have Duncan Hale-Sutton, who managed to image the same thing from up in Norfolk. Now, my friend and colleague Dennis Brzezinski lives up near the north coast of Scotland, and I set up a aurora camera for him. Could we have the lights down a bit, Colin, please? Or in fact, make them completely dark, because nobody wants to see me, they want to see the pictures. So I set up a camera for Dennis, which basically runs through the night, and this is a recording December the 1st aurora, just basically showing the kind of activity Dennis has to contend with. So he's busily trying to take comet photographs, and he's got light pollution from this aurora. The other thing is that there's kind of local internet groups that say there's a fantastic aurora to see, and everybody wants to see it from the lighthouse, which is on the end of the peninsula where Dennis lives. So in the early evening, whenever there's an aurora, there's lots of cars going up and down. But then by this time in the morning, 2, 3 o'clock in the morning, there was no traffic, everyone's gone to bed by then. But you get an idea of how long that aurora lasted for. It basically lasted from dusk right through till dawn. A really impressive event, and got some lovely photographs submitted of this aurora. So this one from Jimmy Fraser, just down the road from Dennis in Alness, showing it rather nicely. And then this one, which I think is really spectacular. So Alan too takes fantastic pictures of aurorae, but he also has got a wonderful artistic eye and takes, I think, probably some of the most spectacular pictures of aurorae with all the foreground details. So this is just an example of that from Moray. So definitely if you want to see aurorae, the best place to be is northeast Scotland. You're at the right latitude there, and northeast Scotland does seem to have remarkably clear weather. I mean, I've been very frustrated the last few weeks with the weather down here in the southeast of England, and Dennis has been taking pictures of comets almost nightly. In fact, he's much better clear skies there than they have down in south of Spain, where some of our robotic telescopes are. So that's that, and then of course Callum moved even further north. He moved up to Orkney. And this is an example of a video he sent me of that same aurora. Quite a lot of cloud around, but a really nice time lapse. It was a moonlit night, hence the cloud being quite bright, but a really nice time lapse. And this also includes some real-time video taken with a Sony Alpha 7S camera, which is the camera that nearly everybody uses for real-time aurora video. You'll see that in a minute. Just showing really kind of how dynamic aurorae are. So you're used to seeing them in time-lapse. So yeah, that was a nice meteor there you might have seen. So this is actually real-time video of the aurora. And anyone who's seen the aurora or the northern lights will tell you the difference between seeing it in a photograph or in a time-lapse and actually seeing it with your own eyes is that with an active aurora, it's incredibly dynamic. Things change very, very rapidly. And so usually most of the photographs you see of active aurorae, all that activity is blurred out by the motion of the aurora. So there will no doubt be more aurorae coming up. I've noticed that I've got a set of colour cameras that monitor the sky continually, and I have picked up these aurorae on those cameras, even from Chelmsford, where I've got a lot of light pollution, because the cameras are just very sensitive to the wavelengths of light from the aurorae. So going from aurorae to another object in the sky, which is a little bit brighter. This is our friend the moon. That has been causing us problems recently, being very bright in the sky. We're coming up to new moon now, which is really good because we're coming up to the Geminid meteor shower, which I'll mention later. And we've got some really interesting comets to observe, and having the moon out of the sky is a good thing. But the moon is a fascinating thing in itself. And Tony Cook sent me some interesting stuff you can do with the moon. If you're interested in looking for meteors, but not in the Earth's atmosphere, but on the moon. So meteoroid impacts or small impacts on the moon have been picked up by people videoing in the Earthlit, the Earthshine region of the moon. And the best times of doing that clearly is near to new moon, when you can access the moon and it's got a large part of its surface not lit by the sun. So if you have the ability to video the moon at sort of 10 frames a second or 20 frames a second or so, at certain times we've got some good meteor showers coming up. They intersect the moon just as much as they do the Earth. So it's worth doing that. If you have these modern cameras which have got GPS time codes in them, that's great, because essentially you can then video the moon. Your images, your video can be correlated with other video from people taken in other places, and that eliminates just flashes that come out of the electronics of your camera. So definitely something worth doing, in a way of kind of monitoring meteor showers on another body in our solar system. The moon, of course, itself is a fascinating object. I've got a couple of pictures of craters which I want to show you. So this crater up here, this is a really nice picture by Dave Finnegan of a crater called Archimedes, which is a crater which has been pretty much flooded with a lava. So it has a very flat floor with little craterlets on it, but a really nice high-resolution image here. And then this crater down here, near the limb there, is a crater called Langrenus. And Bill Leatherbarrow, who unfortunately isn't here, he's had to go off due to the trains, took this fantastic picture of Langrenus. Now, Langrenus is a crater near the limb of the moon, so it's heavily foreshortened. But Bill commented it would probably, if it was nearer the center of the moon, it would be worthy of a much bigger, a much similar crater called Copernicus. So Langrenus is actually bigger than Copernicus is, has very similar features. It has these terrace walls, it has the central peak, and it's just a really impressive crater. But it's somewhat diminished by the fact it's near the limb, and we only ever see it really foreshortened. So anyway, we're coming up to new moon now, and so we can start looking at the sky without the moon's interference. And if you happen to live anywhere away from sort of towns and cities, the Milky Way, the summer Milky Way that we're familiar with, so the Milky Way going down through Cygnus, down into Aquila, is setting away in the west. We still have Vega, which is a star I always consider to be a kind of star of the summer, going down in the west. And I'm particularly interested in Vega at the moment as a star because there's a really fascinating comet at the moment, just a few degrees away from Vega. And as you might guess, I might cover that a little bit later. In terms of planets, what have we got visible? Well, in the early evening, we've got Saturn and down in Aquarius, and here's Saturn. The rings are gradually closing up. So if you have a look at Saturn this year, you'll see it looking like this. Next year, the rings are closing up, and in 2025, we actually go through the ring plane again. Saturn, unlike Jupiter, doesn't generally have much going on in its atmosphere, but there is this anticyclonic vortex, which you can see there, that little black dot in the top there, which is something that's getting Saturn observers really excited about observing Saturn. So if you do get a chance, if you're out with the telescope in the early evening, turn it at Saturn. Saturn is always an amazing object to look at. If you've got people around over Christmas and you want to entertain them, rather than them sitting inside watching TV and sort of sinking into the sofa, get them outside, get the telescope out, show them Saturn through the telescope, and you'll probably have converted them to astronomy for life. It's the planet I remember seeing first through a telescope when I was a young lad, and I was just amazed. It's a phenomenal thing to see. Here's a picture by Peter Tickner, same again, showing Saturn. It doesn't come out anywhere near as good on these projection screens as it does on the website. So I suggest you just go and have a look at the members' pages on the website, where you'll see these pictures in their full glory. Of course, the planet that's dominating the night sky at the moment is Jupiter. Can't really miss it. It's the brightest object in the south, sort of around mid-evening, late evening. And Jupiter, again, is a planet which just shows amazing detail. And John Rogers sent me this, and it's really impressive. So what this is images of Jupiter taken by two observers, but one Jupiter rotation apart. So what you've done here is you've effectively frozen the rotation of Jupiter. And you're seeing it one rotation later, which is about 10 hours or so. And if you look at this, you can see so much going on. You can see stuff rotating around the red spot here. You can see things moving relative to other things. So this is a really impressive. When you actually see Jupiter rotating, you don't see this immediately, but this is actually processed so that you actually are seeing movement in Jupiter's atmosphere with the rotation frozen. And just again, amazing resolution too. Here's another image showing Europa, one of Jupiter's moons, up there in the corner going in, taken by Martin Lewis. Again, amazing resolution on this planet. And of course, not forgetting visual observation. So as was mentioned earlier on, Paul is gainfully continuing the tradition, which is a very strong tradition within the BAA of doing visual observation and drawing of planets. And something I think which we really should continue, because it links modern images in with the historical stuff that John was talking about that's going to be in our archives. So I thought I'd show this because this is from Chris Hooker. So Chris is taking really good, fantastic images of Jupiter, but one of the things that Chris has specialized in recently, and which was mentioned earlier again, is using a sodium filter to image various objects in the solar system. Now, it used to be that we used sodium filters to block out the light from sodium street lights. But if you get the opposite kind of filter, which is a filter which passes the wavelength of sodium D, you can see all sorts of interesting things. And Chris has really beaten a path to this, but other people can do this too. You just need to follow the techniques that Chris is doing. He started this with observing the sodium tail of Mercury, which is a pretty amazing thing, but he's gone a step further to the really truly amazing thing of managing to image the sodium tail of Io this close to Jupiter. So essentially, you're trying to image a very, very faint sodium tail of a moon with a very, very bright planet there. So he has an occulting bar. You can see here, this is Io, this is its tail. And in this sequence, you can actually see the tail moving relative to Io. Again, it's not so easy to see in the projected images. Have a look on the website. But a really amazing thing. And Chris is really sort of beating the path for this. And I think this is an area where there's lots of potential observing to be done. I'm not sure, actually, once you've done Mercury sodium tail and Io sodium tail, and maybe you've imaged some comets which maybe have some sodium in them as well. I'm not sure where you go after that, but I'm sure Chris will have all sorts of good ideas of how we can use those filters. Okay, so the morning sky at the moment is dominated by Venus. Any of you who've been up before the sky gets too bright in the morning, or even after it gets bright, will have noticed that Venus is very, very bright. It's moving downwards again. It's gone past greater eastern elongation, and it's moving very slowly towards superior conjunction. But it doesn't get to superior conjunction, I think, until next, is it August or something? Yeah, something like that. It's a long way away. Because of the geometry of Venus's orbit, it moves very, very fast when it goes through inferior conjunction and out through the crescent phases to half, to dichotomy, but then much more slowly as it's moving away from us. And so it's currently a gibbous phase, as you can see, again, in Paul's drawings here, with some details on the cloud tops of Venus. And we did recently have an occultation of Venus by the moon. And I don't know about you, but I set up in my back garden, expecting to be able to observe this. It was actually a really nice, clear morning. It started off, and then it clouded over, and then it rained, and then it cleared a bit, and then it rained, and then it cleared up a bit. And about 5 minutes, so I didn't see the immersion, I didn't see it disappear behind the moon, but about 5 minutes before immersion, I was thinking, oh, sky's beautiful. It was beautifully clear blue sky, but I could see in the distance this cloud coming. And the cloud arrived 2 minutes before Venus was due to come out from behind the limb of the moon. And I just managed to snap this shot as the cloud was going past once Venus had actually come out again. So that was a really good example of the kind of stuff we have to put up with in astronomy. But Peter Tickner was luckier in Berkshire and managed to get this really nice view, high-resolution view of Venus coming out. Is this? No, this is immersion, so this is going in behind the moon. So you've got the phase of Venus there, and you've got the limb of the moon. And Pauline Phillips also managed to get a view. You obviously had clearer skies than I did, Pauline, when it came out. Yeah, it's a little bit after immersion, that, isn't it? But yeah, it was still there. So that was an occultation of Venus by the moon. We have another really interesting occultation coming up now in a few days' time, and it's this one. So this is an occultation of Betelgeuse, a star which actually subtends quite a large real apparent angle, a huge star, by an asteroid. This is a really rare event. As I understand it, I think Alex is in the audience, as I understand it, the astrometry is really high quality now. So this track is very, very, very good. So if you happen to have, either if you're going to be down in Spain in the next few days, or if you happen to have an automated telescope that's down here in the south of Spain, and there may be some people who just around the southern track of this, and your camera is capable of doing effectively high-speed photometry, which you might do either by reading it out very quickly in a small region of interest or by actually using some drift scanning, this would definitely be an event worth observing. It's a very rare event, as I understand it, a large asteroid occulting a star like Betelgeuse. And this should give us information on the atmosphere of Betelgeuse and its size and shape and all sorts of interesting stuff. So we've got to hope that the weather down in southern Spain improves over what it has been over the last few weeks. We have, a number of us have been trying to use remote telescopes down in Spain, and the weather has been absolutely awful for the last couple of weeks, hardly any clear skies at all. It wouldn't be the Christmas meeting if I didn't, whoops, have things like this. It's been a bit of a tradition in the Christmas meeting. It's been a bit of a tradition in the Christmas meeting that I have a bit of a moan about the fact that journalists will not use proper units to define the size of things. So the human race has spent years and years and years, coming up with precisely defined units for length, mass, all that kind of thing. Whereas journalists think that none of you can cope with that, and so they give dimensions in terms of stupid stuff. Now, this all started a few years ago when somebody used giraffes and king-size beds for the dimensions. And I think this is going to be the last year I do this, because I think a certain journalist in a certain publication is doing this on purpose, just so that they get into the BAA Christmas sky notes. This guy, Aaron Reck, I think, has got form here. So this first one, new asteroid the size of 27 pandas, could hit the Earth in 2046. And exactly the same guy in the same publication is measuring asteroids twice the size of the Super Bowl trophy. So I think this is going to be the last year that you get what I call non-technical units, because I think I'm being taken advantage of by certain journalists who just want to get publicity for their reports. But I will continue with my kind of, if I see anything that's kind of a bit more kind of weird, I'll continue including it. And I did rather like this one. So here, this journalist is trying to describe what something 50 meters across is in size. And he tells you that it's the same size as a 50-meter swimming pool. Well, exactly. This is an interesting one, though. This asteroid, 2023 DW, did for a period have what was called a high Torino rating, which was an indication that it may be dangerous, it may impact the Earth. And it was discovered by an amateur, it says here with a small observatory. It's interesting to see what this observatory is. This is Alan Morey, who's set up an observatory in the Atacama in Chile. So his small observatory consists of a telescope that consists of 4 11-inch Celestron Rasa telescopes, and 4 ASI 6200, which are full-frame cameras on his telescopes. So here's a picture of 2 of them just mounted. So it's a really impressive setup he's got, using, yes, it's kind of amateur equipment, but in a very clever way. He uses software written by Daniel Parrott, who some of you may know from if you use a software called Tycho Tracker, sort of automated software for detecting asteroids, and a very, very impressive setup. So anyway, in future, if anyone spots anything that's kind of using dimensions in a funny way, just, if it's slightly unusual, send it to me, but if it's from the Jerusalem Post or anything like that, I don't want to know. Anyway, another organ where I get Journal of Science Record, the Daily Mirror. Right, so I'm now coming to the kind of centre of this talk about the thing that's been keeping me awake for the last several months. Fascinating comet. But it managed to get a nickname in the media as the Devil-Horned Comet. And obviously picked up by this Mirror journalist. And scarily, they do quote me in a number of stories. And I was mentioning this earlier on, that journalists used to have this thing where they would actually call someone up and say, could you give us a quote about stuff? Now all they do is they just nick something you've said off a website and put it in their articles, which I think is a bit underhand. Anyway, this Mirror journalist obviously knew what they were talking about, because experts reckon the rock will be about the same size as Halley's Comet, maybe a bit bigger, which was last seen with the naked eye 80 years ago. I didn't realise I was that old either. So there you go, that's factoid number 1. This one's good. As it gets closer to our planet, the comet is expected to keep exploding. They like exploding, but don't worry, the bits of the exploded comet will stay in outer space and won't return until 2095. Well, that's kind of, yeah. Plus, it's not the most explosive comet in our solar system. Which is the most explosive comet in our solar system, Richard? 29P, I guess. Yeah, when it swings by Earth, it'll be about 144 million miles away, so there's little chance it will affect us. Well, it has affected me a lot. It's meant that I have had many nights with no sleep and a lot of work, but it's a fascinating comet. So this is 12P Pons-Brooks. If you haven't heard about 12P Pons-Brooks, then you obviously haven't been reading the BAA website. It's a periodic comet, as it said, similar orbital period to Halley, 71-year orbital period. Possibly quite large nucleus for your average comet, so maybe the nucleus is maybe 20 kilometres, maybe a bit bigger than that, which is big for a comet. This comet has an interesting characteristic that pre-perihelion, and it's usually pre-perihelion, it has outbursts. So it's been seen many times before. The last return was in 1954. But of course, we now have much more observations of it, much more capability to observe it. And so this plot was done when it had had 4 large outbursts. It's now had 5. And what you can do is you can image the comet. And these images were all taken with the BAA telescope that we have through Maxim Yusatov we use in the south of Spain. So it's called the Alnitak Observatory. It's available to anyone within the BAA who wants to use it. So if you want to use this telescope, you can contact David, and David can explain how it be done through either section directors or another means. But it's a really good facility. It's a 17-inch CDK in really good conditions with a really nice camera on it. So this sequence was taken with that, and you can see here the comet goes into outbursts. You have a bright inner coma, which is dust, and a faint outer coma, which is the gas that has pushed the dust out. What you can do is you can plot that expansion for the different outbursts we've had, and the most powerful outburst we've had so far, the dust coma was expanding at something like 310, 315 meters a second. So this is a really energetic event. What's happening, and Richard can say a lot more about this, because probably there's not many people in the world who know more about this mechanism than Richard does, is that there is a very sudden release of gas which takes the dust up with it. It's kind of in a few minutes almost. And that then expands away into the vacuum of space. And you see there are various features that you can see in this, and they are all kind of baked in to this expansion right at the very beginning, essentially when the initial outburst is happening. So some people have called this dark feature a shadow. It's not a shadow. It's an area where there's less dust, and there's less dust there simply because of the geometry of the way that the outburst has happened. Anyway, it's been an incredibly active comet. This is a light curve of it from the last month. This is the really big outburst that occurred on November 14th, and then there was another one on November the 30th, and Richard has produced this really nice plot of the comet so far, and if you look at that, you might see some pattern. And Richard has speculated that that pattern is associated with the rotation period of the comet nucleus, and it's something like 15 days or so. So if you're interested in detecting the next outburst, get your telescope out somewhere around December the 14th or 15th, and you may be lucky to be the person who detects the next outburst of this object. But a really fascinating object, and we've had lots of observations submitted. I was lucky enough in the really big outburst to be imaging it just after the comet went into outburst. And if you plotted the light curve, as I do here, you can see there's actually a change in slope of the light curve, which is either due to a second outburst occurring very shortly after the first one, or some other thing to do with the physics of the expansion of the dust. But loads and loads of stuff here, and loads of stuff to keep Richard busy doing his analysis, I think, for quite a while. It's just a fascinating comet. This just shows the astrometry, so the measure of the position of the comet, just to show that the comet's not been, it's a big nucleus, it's not being disturbed by these big outbursts. You can see that essentially what happens when there's an outburst is the astrometry goes off. It should be about 0 here. It goes off, but that's because the measurement of the centroid of the comet is biased by the fact you have this bright outflow of material, but then it returns back to where it should be. So there's no sign at all that this comet is suffering from these outbursts. It's a big comet. It's not fragmenting. It's not having its orbit changed. But it is a really interesting thing to see in the sky. And after the really big outburst that we had on November the 14th, Paul actually made a visual observation of this, and he sent me a text message that I can't... Did you call me? Oh, you did, but you also sent me a text message, I think. It was something like, my God. So here was this kind of suddenly appearing globular cluster.
I actually spent 10 minutes looking to see if it was an MGC or something.
Yeah. Yeah. So if anyone's interested in observing this, just keep your eye on the BAA website or sign up to the BAA Comets list, and we get the earliest notification there of these outbursts, and just go out and have a look visually. That night, I did go out and look visually as well, and I saw it too. Quite an amazing thing to see. At that point, it was bright. It was about 9th magnitude. It was compressed. All of that was compressed into a very small area. It very quickly becomes much more difficult to see as it spreads out. So here's an image taken with the Alnitak telescope. That inset there shows details of the outflows, mapped using a thing called a Larsen-Secunina filter. And you can see just faintly on this, there's a little bit of a tail up here, which is much better shown on this Peter Carson image there. So this is the tail going off up here. Great object for spectroscopy. So Robin Leadbeater took a spectrum of it and sent me an email saying, well, basically it's dust. So the spectrum just shows reflected sunlight primarily, but a really, really interesting object. And loads of pictures from people. So this is Tim Haynes. This is just before the last outburst. You can see this is the comet with its coma from the previous outburst. And then on the next picture, which is taken by this one, Richard Sargent. This was on the night of the outburst, and you can see it's much brighter in there. So this comet is outbursting almost, continually. This one from David Strange, again showing it with the green gas coma around it. And then this one from Peter Tickner, I think this one is, again showing details within the inner coma. So a really fascinating object, which shows up really well at all sorts of scales. So this is Mazen Younis' picture taken from his remote observatory in Morocco. Again, showing the tail. This is in a different orientation. Tail's down here. I'm not sure you can see it on the screen. But have a look on the website to see those. And then this one, the most recent image I've got from Dennis, from the clear skies up in the north of Scotland, showing all the detail. You've got the inner dust coma from the previous outburst, you've got the structures, you've got the tail, you've got the outer coma, and then surrounding all of that, you've got a much fainter coma from all the previous outbursts as it accumulates. So this is just going to be a fascinating comet to follow. It's just passing Vega at the moment. It's going to move down through Cygnus, through Andromeda, through into next year as it heads towards perihelion in April. It could get to 4th magnitude, maybe even brighter. One of the interesting things is that it will be in the sky at the time of the total eclipse, next April the 8th. And should it have an outburst, it might be quite an interesting object at that time. So it may be a really interesting, well, it is a fantastic comet, but it may be an even more interesting comet as we approach perihelion. Of course, there's another comet which we've almost kind of forgotten about in outbursts. I know Richard hasn't, but we almost have, and that's 29P, which is the comet which is the sort of comet we always think about as having outbursts, this really big comet out in the outer solar system beyond Jupiter in a circular orbit. This one's got a much bigger nucleus, probably about 60 kilometers or so across. It also has regular outbursts. Similar mechanism, is it? I think, Richard? Yeah. And observers have been monitoring that. And here is the very latest news. There was an outburst detected by the Comet Chasers group on December the 8th. So that was yesterday. So again, another interesting object to observe in the comet world. And then before I move off comets, I just wanted to mention this one, which may be another interesting comet in the comet world. So I've mentioned this one before. This is 2023 A3, Shuxinshan Atlas. It was a comet discovered a very long way out in an orbit that's going to bring it in very close to the sun. So alarm bells should already be ringing there, because what happens is people try and predict the magnitude from stuff when it's a long way out and say, oh, it'll be brighter than the sun when it comes into the inner solar system. So take this with a pinch of salt. But this comet has been in conjunction. It's not been observable for a while, and we have now started getting images of the comet as it's coming out of conjunction. And it's looking really healthy. And so here is the latest light curve from COBS. So here we are. These are the latest observations. Okay. And you can see that the predicted magnitude at perihelion is potentially negative. Big pinch of salt, right? But we are beginning to get potentially a bit more confident that this is going to be a nice comet. Don't book a holiday on the basis that it's going to be -3 or something. But it's going to be a nice comet. It's going to be, it could be a nice comet. It's going to be difficult to observe before perihelion because it's going to be very close to the sun in the sky. But after perihelion, it comes out of the western sky in mid-October next year. So maybe I'll be standing here in November showing some fantastic pictures of an incredibly bright comet in the twilight sky. Maybe I won't. But it's the best thing we've got at the moment for being a really nice comet next year. Say, don't book a holiday on the basis of it, but if you're going to want to go to the Canaries for any reason anyway, you might as well choose to go there in the middle of October, just in case. So that's comets. Just talk a little bit now about stuff that comes off of comets. Last time in Sky Notes, John was here talking about these, the Andromedids. So these are the meteors from comet BAA. And there was a prediction that on December the 2nd, there would be an outburst of these meteors. Well, predictions are predictions, and science moves forward by negatives as well as positives, and there was no outburst. So what this plot is showing is it's showing the radiance of all the meteors picked up by the GMN camera network, color-coded in terms of velocity, with faster meteors as orange, slower ones as purple. There's a little cross here, there, yeah, which is where the predicted radiant was, and there is no clump of meteors around that radiant. So it didn't happen. And scientists, being good scientists, apparently have already modified their theories now to predict that there wasn't an outburst on the 2nd of December. But that there will be an outburst some other time. So this is rather nice. So I was playing around with plotting the radiance from the GMN database. And basically what you've got here is, this is looking at the Earth from the outside. This is declination up this way, right ascension that way. You can see the clumps of different meteor showers as they move across the sky. You can definitely see here that the radiance change with time as we move around the solar system. And we're coming up, so this is coming up to December now, and you'll see there's a big red clump that appears just about there. That big red clump, which is already appearing, is the Geminid meteor shower. So here they are. So this is the meteors that were detected by the cameras on December the 6th. So the Geminids is a really good shower. It's probably the most active shower of the year that we have. This year, we're lucky that the Geminids will be seen in a dark sky. So the moon is out of the way, which is really good. So the Geminids can be seen over a long period, but basically the maximum is on the night of December the 14th. So we've just got to keep our fingers crossed that we get clear sky that night. Last year, it was kind of a mixture of cloudy and clear, and the moon was in the sky. And my cameras one night, on maximum night, when it was only clear for about half the night, got about 300 Geminids per camera. So I got over 1,000 Geminids in one night. It's a really good shower. It's the one shower of the year, well, apart from the Perseids, which is in the summer, which is nice to go out and watch. It's the one shower in the year when it's worth actually going out in the cold if you want to show some friends some meteors, because you're almost on maximum night guaranteed to see something if it's clear. Right, we'll leave comets and their debris behind and we'll come to variable stars now. So I'm going to mention two variable stars, and they require you to be a little bit dedicated, because if you're going to see these variable stars well, you need to get up before it gets light in the morning. And that's always a challenge at this time of year. But the constellation they're in is Corona Borealis here, which is really best in the morning. You can just about catch it at night, but it's really low down. And the two stars are these. So T Corona Borealis, which Jeremy mentioned a while ago, is on the verge of going into outburst. And as Jeremy told us when he gave his talk, the precursor to it going into outburst is it has a fade. And we are seeing that fade now. So here's that fade of that star. So the outburst is due, I think, sometime February to August next year. So this is a star really worth keeping an eye on. It's worth getting up in the morning now and just monitoring through this. One of the reasons there's quite a lot of scatter on this is that the star itself has a variation which I think is due to the precession of the physical rotation or something, isn't it? Is it? Right, okay. Right, so you have on top of the kind of general going up and down, you have this 227-day period due to the star's shape. But a really fascinating star, and you know, a star that you can monitor with a small telescope, because it's a fairly bright object. You just need to get up early. The other star is also in Corona Borealis, our Corona Borealis, which we've mentioned many times before. A star that basically sits at about 6th magnitude and then suddenly dips down for a reason of sort of the opaque material in front of it, and then has recovered. So it had this dip, and it's now in the process of recovery, but you never know quite what it's going to do next. So another really interesting star to keep an eye on. Then Callum on the website has a regular deep sky update and has objects of the month to observe, and the one from last month is this, which is a planetary nebula, IC 289, which is sort of perfectly placed at this time of the year. And here's a rather nice drawing of it by Martin Fode. Martin Fode's drawing of it. And then Richard Sargent took an image of it too. And then this month's object is in Auriga, I think, yeah, B34. It's a dark nebula in Auriga. So here it is, that dark cloud in front of the stars. And this is rather a nice image taken by Ian Cartwright. So again, if you're looking for interesting deep sky objects to go and observe, go and have a look on the website, have a look at the deep sky section and the object of the month. It's always a good thing to go at because you can then compare your observations with other people's. So just drawing to a close, and I don't want to keep anyone much longer because the drinks reception is coming up. Stuff that's much closer to us. I just wanted to show this. So we all have a bit of a kind of hate relationship, I guess, with Starlink satellites. Mine is a bit kind of more nuanced because I work in the business of this. But I have found them particularly annoying recently. So this is a video from my Meteor camera. It's a time lapse. And it shows an interesting feature of what Starlink satellites do. So normally these Starlink satellites are flat tiles, and they fly with the flat tile pointing down to the surface of the Earth. They're shiny, and the idea of them being shiny is that means that they don't scatter much light off to the side. So that's a way of keeping them fairly dim. But in certain geometries, and these geometries are in the western sky at twilight and in the eastern sky in the morning, you can get glints off these satellites because the sun, which is over the other limb of the Earth, is actually reflecting off the base of these satellites. And so what you can see is you end up with loads and loads of Starlink satellites that kind of are gradually moving down as the sun moves down. Now, this is a bit of a problem if you're trying to image a comet, which is in the western twilight, which the best comets usually are, but it's where 12P currently is. And I thought I'd show this. This is a sequence of images I took of 12P a little while ago with a wide field telescope. So all of those traces across there are Starlink satellites. And if you take any images now in the western or eastern twilight sky, which is where the best comets will be, they're just covered with these things. Now, you can process those images with a thing called a sigma clip stacking. And this particular stack here, I processed using that technique, and here's the result. So no satellites, right? And the reason that works is essentially the software stacks each pixel, and within each pixel it looks for outliers, so things that are too bright for that pixel, and it rejects them. And that works really well, but it's just a real pain that you have to do it, and particularly on wide field imaging now, it's becoming a real problem. So, you know, I don't think we're ever going to stop these mega constellations because they have too much positive from a societal point of view. I mean, Starlink has been used a lot in the Ukraine situation to maintain communications in Ukraine and in other places. So you're not going to stop that, but we do have to keep pressure on these companies to mitigate the effect. So try and keep the satellites as faint as possible. And for images, we do need to sort of investigate the techniques that we need in order to be able to remove these things from our images. So yeah, Starlink satellites are a pain, but there's even more junk up there because one of the astronauts on the space station dropped a tool bag, which became an independently orbiting satellite. And remarkably, it's big enough to actually have its own designation. So this tool bag is 1998 067 WC. So 1998 is the year that the first bit of the space station was launched. And 67 is presumably how many bits have fallen off it since then. So this is a picture of the tool bag, which is, you know, the size of a tool bag, going around the Earth in an orbit 400 and something kilometres up, taken by Nigel Evans, who's sort of specialised in taking pictures of strange bits of junk in orbit. Yeah, kind of interesting to see. So I'm just going to close, and I've been kind of talking about Starlink and obviously SpaceX and Elon Musk. I just wanted to show you this final video because, and I hope you'll forgive me this because it's not really astronomy, but I'm an aerospace engineer. I'm just amazed by some of the things that Starlink has done, and some of you may have seen the recent launch of Starship from Texas. And SpaceX have just released this video, which I think is pretty amazing. So I'll just run this for a couple of minutes and then conclude, and then we can go and have some drinks. So this is Starship. Is this going to run? I hope it is. Yeah. This is Starship.
Attention all operators on countdown.
The Saturn V was shorter than this and had half the thrust and half the mass. So this is twice as heavy, twice as much thrust as Saturn V.
Stage 1.
Just an incredible thing.
Go. Copy, go.
And this video is pretty amazing.
Clock is rolling. 10, 9, 8, 7.
33 Raptor engines.
5, 4, 3, 2, 1. We have liftoff.
So this is the first time they've tried what's called hot staging, which is they fire the second stage engines before detaching from the first stage, which is just about what's going to happen here.
Boost stretcher cut off.
And then the first stage was supposed to turn around and come back, but it suffered what they call an RUD, a rapid unscheduled disassembly. And the second stage, the Starship itself, going on, you can see it's got 6 engines. It also suffered a RUD before it got into orbit. But it's getting really close now, I think, to this thing being a serviceable spacecraft. And NASA is almost relying on this to do some of the exploration of the moon. So, you know, whatever Elon Musk has done, and there's lots of stuff he's done that's not so good, Starship, Falcon 9, and Teslas, mostly, are pretty good. So that's my Sky Notes for this year. Happy Christmas, everybody. If you get a chance, get out, watch the Geminids in a few days' time. If you do get a chance, go and have a look at 12P as it's going through its outbursts. Loads of things to see in the sky. Have a great Christmas. Have a really enjoyable time. If you get a chance to show other people astronomical objects over Christmas, that's the best way of getting them into this subject. And see you all in January. Thank you.
Thank you very much, Nick. Thank you very much to our other speakers, and thank you very much to Hazel Collett for organising a fantastic meeting. It's lovely to see so many people here, and if you can stay around, there will be some refreshments outside, and the place is open until 7 o'clock, so we can stay here until 7. So thanks to the IOP for exceptionally allowing us to stay here on a Saturday evening. And I hope to see you all on the January meeting on the 20th of January. Thank you very much.